So good morning, everyone, and welcome to the FAA Data Challenge Finale event. I am Marcita Dill, Acting Chief Data Officer, and I'd like to welcome all of the students and advisors and professors here today for getting to this point. All of the work that you all have done up to this date has allowed you all to be finalists in today's competition. The journey started for you all. Hasn't quite been a year, but the reason that you're here today is because you answered a call for ideas where we were soliciting students and universities to allow us to explore the use of AI and advanced analytics to solve a number of key areas, including improving safety, operational efficiency, sustainability, and also the introduction of new entrants into our national airspace. So I'll say to all the teams, relax. I've assembled a panel of subject matter experts from across the agency and also our partners. And they're here today because they think it's important to invest in the future, and they also see the benefits of what might be through the ideas that you all present today. I wanted to thank MITRE for hosting us today. This teams had an opportunity yesterday to visit some of the labs here at the MITRE facility. And I hope you all were able to see not only the cutting edge projects that are underway, but also an opportunity to interact with some of the researchers that are involved in those projects. So I hope that you saw yourselves as you experience the tours, and hopefully one day you'll either be in one of our labs or leading one of our aviation research projects. Thank you to Jamie and HeroX, who have been interacting with you over the past several months and also coordinating today's event, along with Steve Boguski, who works in the Chief Data Office with me as well in coordinating today's events and also the planning that's underway. So before we get started, I'd like to introduce our steering committee members. Some of them are here in person, others have joined virtually. So I am going to call each one of them out by first name, and I'll ask them to either come on camera to introduce themselves or unmute their mic so that they can say a little bit about their background and where they work in the agency or which industry partner they represent. So first up is Jason.
Hi, I'm Jason Johnson. I work out of ADE on the mission support side for the tools and management section, and just recently the special programs unit. Congratulations, guys. Good work.
Thank you, Jason. Caroline.
Good morning, everyone. I'm Caroline King, and I am the Senior Statistician within the FAA Office of Civil Rights, and I'm happy to be here. Congrats to all our finalists.
And Shebnam.
Good morning, everyone. I'm Shebnam. I'm with Stephen Morcetta in the Chief Data Office. I'm a data scientist, and my background is actually in mathematics. I just want to say that you all have done a really excellent job with all these proposals, applying mathematics and data science techniques to complex challenges. It's been really a pleasure for me to read and vet your scores, and I look forward to understanding the thought process that went behind your project. So this has been really exciting. Thank you. Great job.
Thanks, Shebnam. Tony.
Hello, good morning. Great submissions all around, and congratulations. I'm Tony Hybe. I'm the manager of the business intelligence team under aircraft certification, and that's under the aviation safety branch.
Mike.
Hello, good morning. I'm Mike Paglione. I'm the manager of the Aviation Research Division out of the Office of NextGen here at the Technical Center in New Jersey. Very excited to hear your briefings. It was very interesting reading your reports.
John.
Good morning, everyone. I'm John Berdimo. I'm currently the Director of Performance Analysis and the Systems Operations Services in the Air Traffic Organization. I'm also the Air Traffic Organization's Data Champion. It's been an absolute pleasure. It's my second year working with the University Data Challenge. And thank you to Marcita and the team for continuing this even through these very interesting times. Looking forward to the day. Thanks.
Steve?
Hello, I'm Steve Bogutsky. I work in the Chief Data Office with Marcita. We manage analytics, enablement, and business intelligence for the FAA. So we enable all the artificial intelligence technology for everyone in the FAA. Also, echo everyone's excitement about your proposals and look forward to learning more. Thank you.
Atusa?
Good morning, everyone. This is Atusa Ghafouri. I'm a manager for the Automation, Evolution, and Infrastructure branch and working with NextGen Office. I'm very excited to be here and looking forward to learn more from all the participants. Thank you.
Thanks. Aruna?
Sorry, everyone. The video is not turning on. Give me a second, please. I'm sorry. Hey, good morning, everyone. I'm Aruna Ganreddy from the Office of NextGen, NAS Lifecycle Planning Division. Good luck to everyone, and I'm looking forward to listening to all your project briefings. Thank you.
And Gabe?
Good morning, everyone. I'm Gabe Elkin from MIT Lincoln Laboratory. I'm an assistant leader of our air traffic control and weather systems group here, and we're an FFRDC like MITRE, and we've been supporting the FAA since about 1971.
And now I will move to the folks in the room. I'll start with Dr. Eugene.
Good morning, everyone. Eugene Mangordi with the MITRE Corporation. I'm the group leader for the AI Safety Intelligence and Assurance Group at MITRE. I also manage the Aviation Safety Information Analysis and Sharing program. And it's been a privilege reading your work and really looking forward to hearing more from all of you today. Thank you.
Great. And Dr. Craig?
Hi, this is Craig Wanke. I'm the chief engineer for MITRE's Center for Integrated Transportation, in which we do our aviation and ground transportation work. And as Eugene said, I was really neat to see the various approaches and the really creative ideas that you guys came up with. So I'm looking forward to hearing more about it. Thanks.
And finally, Dr. Deere.
Good morning. My name is Michael Deere. I'm the acting manager of the Safety and Performance Analytics section in Aircraft Certification Service. Welcome.
All right. So as you can see, we've assembled subject matter experts that represent different areas of expertise. They will be listening to today's presentations, and they will also we will also allow time for a Q&A session at the end. And best of luck to each of the teams, and we will get started shortly.
All right. Thank you, Marcita. Thank you to all of our steering committee members. Thank you to all of our teams. Echo the congratulations for being here. This is very exciting. So we're going to get started with the presentations. So bear with us. We are going to try to keep time with what's on the agenda. So the format, we will call each team up. They'll have a minute to set up and get started with their presentations. Each team will have 15 minutes to present, and then there will be 8 minutes of Q&A. So we will take questions from our steering committee members first. And if anyone online has questions throughout the presentation, you can submit those questions using the Q&A pod in Zoom. We will also take questions in the room. So we will get started. Our first team is Binghamton University, assessing flight delays using weather predictions.
We good to go? Good morning, everybody. We'd like to first start by thanking HeroX along with the FAA for putting on this competition and bringing us all here together for today. I know we all really appreciate it. We'd also like to take a moment to thank MITRE for hosting us these past 2 days, along with the laboratories, and we all had a great time. I'm sure you all did too. We are Binghamton University, and today we'll be presenting our project on assessing flight delays using weather predictions. So to kick things off, we'll start with a quick team introduction of who we are and what we do at Binghamton University. Then move on to defining our problem, which is mitigating weather delays in airports. From there, we'll dive into a little bit of the background of how this problem is currently solved, along with the goals we hope to achieve. And then we'll dive into the fun stuff with the solution definition. We'll give a breakdown of the model we've developed, along with its associated benefits. And from there, move into our methodology, where we'll introduce the machine learning techniques we used, and then we'll move into our testing procedure, which we used to generate our results. Then we'll go ahead and present our final results along with our key findings, and then finally conclude with some future work of how we hope to expand and improve the model in the future. So kicking things off, I'm Benjamin Deibler. I'm currently a junior at Binghamton. I'm an industrial engineering major, and I was the team lead for this project.
Hi, my name is Gerard Dutan. I'm a PhD student in the System Science Department at Binghamton, and I serve the role of being an advisor and constructing the framework for how we kind of solve our problems.
Hi, my name is Lily. I'm a junior here at Binghamton, and I study math. And for this project, I mostly worked on the weather prediction.
My name is Nicholas Ingrassolino. I'm a junior in industrial and systems engineering, and I was in charge of the rescheduling process.
My name is Justin Mintz. I'm also a junior in industrial and systems engineering, and I worked on the delay assessment portion of the model.
So for this project, we looked at LaGuardia Airport, which is the busiest airport in the country. On one day, over a quarter of the flights were canceled because of heavy rain. Another fact is that LaGuardia is the third in total time delay due to weather. And over a 5-year period, almost 3/4 of total delays that were significant in time, that were over 15 minutes, had to do with weather. So because of this, in order to look at how to make this airport more efficient, we wanted to see how we could mitigate airport or weather delays.
So typically what is done to solve this problem is use some sort of weather forecasting and then apply a delay assessment to determine what times there should be delays, and then go through a rescheduling process. We made our own version of this based off of research with IEEE, and that's going to be used as our basis of comparison to our model.
So before we get into the specificity of the methodology we use, we first like to define the goals and motivate what we're trying to actually solve. So some of the things that we'd like to get to is be able to alert affected personnel with enough time so they can mitigate their procedure due to a delay. We'd also like to cursorily identify weather delays and accurately predict weather as a consequence of our model, improve takeoff efficiency, and really make this a practical model. So we wanted to construct something that could be used. So in order to do that, we made sure that the computational time at which our models would run would give us the semblance of real-time operational mode. So those are the main goals of our project.
And so getting into the scope and assumptions, we had a scope to reschedule departing flights based on the predicted weather. And so since we're looking at just the predicted weather, the only delays that we would be considering is the weather delays. Similarly, since we're looking at departing flights, the only weather to start out our research that we'd be paying attention to is of our observed airport, which is our departing airport. Our observed airport, as we had said earlier, would be LaGuardia Airport. And to start out this research, we were going to be focusing on the summertime months, which would be from June to September. We did assume through analysis of our data that flights from LaGuardia can depart at a maximum departure rate of once per minute. And the way that we came to this conclusion was basically from looking at our data and finding that each runway of LaGuardia can handle 1 departure per minute. However, they have 2 runways, but one of the runways is typically used for incoming flights. And since we didn't have the data to prove when both runways were available, we just made the assumption that only one runway would be available at a time. And our final assumption was that weather conditions at the top of each hour would be representative of the entire hour based on the data constrictions that we had.
So moving on, here we have a breakdown of our weather prediction and rescheduling, or WIPR model. Now, at first glance, it seems to follow a similar architecture to the traditional research model. However, we've made a few key changes that we think really improve the results. So the main change we've made is, instead of calculating the delays on solely the predicted weather, we are actually calculating the delays on our historical weather data and then inputting that into an LSTM, which then outputs both the predicted weather and predicted delays in the same step. And then using those predicted delays, we're able to adjust the original flight schedule to account for those and verify that against our predicted weather.
So in implementing the Whipper model, there are many benefits. Most importantly, there's an increase in the probability of the correct weather predictions. Now we'll get into that in a little bit, but a key takeaway of this is that with an increased probability, there's a better confidence in the predictions that are being set. So with this, we can make an earlier prediction with the same degree of confidence as before. And so with this, we can announce delays much earlier, which would allow for the affected personnel to prepare for delays. And affected personnel, I mean any passengers of delayed flights, along with any staff of the airport who would have to prepare for delays. Along with the announcement of a delay, the type of weather which is causing the delay would also be announced. And this would allow for better coordination for the preparation for these affected personnel.
So to train the model, we used two data sets. The first was the weather data from LaGuardia, and we looked at 2015 to 2024. And as mentioned earlier, we decided to only focus on the summer months. So we only used data that came from June through September. And so this data set was in hours for its units. The second data set we had to use was to figure out when flights were actually getting delayed or not. So we also looked at the LaGuardia flight log. This one was sorted by departure time, and it was in minutes for its units.
For the delay assessment portion of the model, the delay is determined throughout the prediction of the neural network, and then that could be explained by one of these conditions. So the delay conditions would be if the wind gust was too high, visibility was too low, temperature was too high, or if there was a thunderstorm. Thunderstorm was a little bit tricky. So there are certain conditions that indicate that there is a thunderstorm. So we just said that more than half of these have to be true just to be on the little bit of a safer end in determining that. And also there has to be some amount of precipitation in order for thunderstorm to be true. On this graph, you can see, and it's an example of a wind gust graph. So this was a day with high wind gusts. So you could see the threshold line there. For the first 4 hours, there would be no delays. But then for the next 2 hours, there would be a delay as those points were over the threshold.
So to predict the weather, we were facing a multivariate time series problem since we were trying to predict a couple of factors a couple of hours into advance. So we were trying to predict things like precipitation, temperature, weather, temperature, visibility, etc. So we decided to use an LSTM, which stands for long short-term memory. The reason this model was nice is because it biases the last couple hours the most. So it's important in the context of weather since the last few hours are a lot more important than what the weather would have been like maybe 2 weeks ago. So for our model, we trained the data from 2015 to 2019, and then we left the last 4 years to test the data on. Our window was 24 hours. So we would look up the 24 hours, we'd put this through this LSTM, we'd have a dense layer that would reformat it a bit, and then the output would be a prediction for 6 hours for each factor. And so this model is quite nice in the result because it's very computationally quick. Because of our choice of an LSTM and the specific times we picked, this whole thing only takes less than a minute to make the predictions for 6 hours. So it doesn't have to be run super far in advance, and it can be run like pretty often.
So the main output from our LSTM are predicted delay times. Now, looking at the raw output across the entire testing set, this data has a lot of noise, and it's pretty hard to distinguish when we should be classifying a delay, when we shouldn't be classifying a delay. However, we're able to perform essentially a cutoff analysis using a value of 0.2, identifying anything above that as a delay and anything below that as not a delay, which can be seen in this graph here. After performing it, this graph shows it's much easier to identify when a delay should be, with a value of 1 identifying a delay and value of 0 identifying no delay. Now, unfortunately, across the entire testing set, we do miss a few delays here and there. However, this is still much better than the raw output from the model, and it's what we used for getting our results.
So after the LSTM does determine that there is a delay, the Whipper model autonomously reschedules flights based on the delay period, and its goal is to minimize the number of delayed flights. So whenever there is a delay period, all flights must be grounded, which means no flights can depart during that time. So any flight that is originally scheduled to take off during the delay period has to be pushed back to take off immediately following the delay period. Subsequently, any flights taking off or originally scheduled to take off immediately following the delay period would then get delayed also. This causes a chain reaction, and this is what we tried to minimize with our Whipper model. So the way that it does this is it looks at the maximum departure rate of the observed airport, which, as we had said in the assumptions, was 1 flight per minute. And so the Whipper model will schedule immediately after the delay period, one flight to take off every single minute. And this continues until the new departure time of a flight matches the old departure time of that same flight, which would mean that there's no longer a delay. And so in implementing our model, there are two types of errors. Type 1 error will occur if there is a predicted weather delay, if there is no predicted weather delay, when in reality there was adverse weather which should have caused a delay. And now this can lead to dangerous takeoff conditions or abrupt stoppages of airports. This can be mitigated through adjusting the cutoff values of the LSTM model. So lowering these values will allow the model to see more weather as adverse, which would lead to more delays. A type 2 error, conversely, will be if there is a predicted weather delay, when in fact there was no adverse weather which should have caused the delay. And so this could lead to unnecessary inconveniences to the affected personnel. Thankfully, this is mitigated through the iterative design of the WIPR model. However, if type 2 error does consist, then we can raise those cutoff values back up, which would lower the effect of a type 2 error.
So in this section, we'd like to talk a little bit about the testing process and kind of be a little transparent with like how we did the testing and what the data set looks like. The bullet point on the left shows this sort of percentage breakdown of what the data points are coming from. So there's about 43% of the days in our testing set that have thunderstorms, another 43% with clear weather, and about 14% with strong winds. We do make the note that temperature and visibility were not tested in the sense that there were no occurrences of temperature that were exorbitantly high at LaGuardia, which would like ground a plane given our threshold values. So it just turned out to be the case that within the 5 years of the data set that we were looking at, those occurrences didn't happen, as well as a visibility issue that would be so, I guess, negative that a plane wouldn't take off at LaGuardia. And so the table on the right is just a distribution across hours at which we're doing our testing.
So here we have a breakdown of how the WIPR model would be used in an actual airport. So the first step is taking our weather and flight data. These are just samples, again, from the data sets that we used. And then this weather is taken and put into the WIPR model, where the first step is calculating the delays on the weather, like we mentioned. And then this is then put into the LSTM, which makes a prediction for both the weather and the delays for the following 6 hours. And then using that delay prediction, we perform the cutoff analysis, which boosts the signal. And doing all this gives us a prediction that looks something like this, where this would be an example of a delay due to high winds, which can be seen in the red there. And then taking these delays into account, we adjust the final schedule, which this is again another example. The red would be an area where we've identified a delay, and then we consolidate those flights later in the day. Now, since we're making a prediction for every 6 hours, we want to be able to update this to ensure we're always looking 6 hours into the future and make sure our prediction is accurate. We do this by taking our adjusted flight schedule and re-inputting that back into the model once every hour, along with our predicted weather and delays. And then since this only takes less than a minute to run, we're able to update our prediction very quickly. And again, this is done once every hour, so we're always looking 6 hours into the future.
All right, so for our results, the traditional approach to this, based off the model that we did make, has an accuracy rate of 80.4% and an error margin of 19.6%. But the improved WIPR model has an accuracy rate of 82.7%, and we reduced the error margin to just 17.3%.
So one way that this model might be used in the future with some additional work is to kind of rethink the way that we create these schedules to begin with. So right now, to prevent delay propagation, which is when one flight causes a lot of future flights to get delayed, buffers are kind of scheduled in so that once a flight gets delayed, those buffers will preemptively kind of take up the time for that delay. One way to rethink this is because our rescheduling process already does this, not necessarily getting rid of the buffer, but kind of minimizing what that buffer is in order to get more flights out, say, every hour.
And some of our other ideas for future work would be to cut the prediction window down to 3 minutes. So right now it's in terms of hours. The only reason that we have it in terms of hours is because finding historical weather data in terms of minutes is very difficult. But once we can make it in terms of minutes, we'd like to go to about 3 minutes, and that's just because it takes about a minute for the model to run, so we want some cushion there. We'd also like to add seasonal variability. So right now it only works in the summer months, but the winter has different weather patterns, so we'd like to also incorporate that. And then the incorporation of additional airports. So having a more complex rescheduling process when one airport has a delay and the other airport doesn't. Thank you guys for your time. I hope you enjoyed the presentation and feel free to ask any questions.
Right. We will now take questions from the steering committee. Any steering committee members can come off mute and put themselves on camera, or here in the room, just come on the microphone, please.
Hi, this is Gabe Elkin. Can I ask a question?
Of course. Yeah.
All right, great. So first of all, great talk. Thank you very much. This is a very interesting problem. And you started to hint at the end what my question was. What do you think? So you did this for one airport, and there's lots of airports. So one question would be, as you looked at future work, what do you think you're going to have to do to your approach, or what are you going to have to change to accommodate the larger complexities of the fact that this is really a network? And so I guess in one sense it's other airports, but then it's also the air traffic sort of apparatus, which includes not just takeoffs and landings, but approaches to going through terminal airspace and en route airspace. And I guess my second question was your weather information. How close to the airport did it cover? So if you said there was a thunderstorm, was that within some vicinity of the airport?
Yeah, so just for the second question, I could answer that pretty quick. LaGuardia has a weather station there, so we use the data from his weather station. Can we go to the hidden slides? I don't know if you want to try.
Yeah, you can go to hidden slides. We're going to. Is it okay if we exit the slideshow to go to the? Should be able to. What one do you want to go to?
For the future work.
Okay, yeah, just let you go for it. I think you have to go into presentation mode to bring it up. I gotcha. One second, sorry guys. There we go.
Okay, yeah. So this is just some extra notes on what we had for ideas when we were thinking about our future work. For the incorporation of additional airport, what we were thinking that it would look like is we would have, say Airport 1 has a weather delay, and then Airport 2, all of their flights that are going to Airport 1 would also have to be delayed. So then we would have to make a new rescheduling process, not only for Airport 1, but also Airport 2, where only certain flights are delayed. And that's kind of the gist of what it would look like.
No, I think the only thing that I wanted to add is that, the reason that we started on this is to your point, right? The dimensionality of the problem really increases, right? As you see this as an interconnected network. And so we wanted to first get the fundamental ML part working correctly, right? Before we started messing with the more convoluted topology of interconnected network systems. But we would be looking, as Justin said, at both interconnected weather predictions to kind of formulate some sort of delay processing between the two of them.
Thank you.
Thank you for your question.
I have a question. How does your model capture long-range dependencies and weather impact on delays? And I guess a sub-question for that is, did you evaluate sequence length limitations in your model? Thank you.
Can you repeat the last part of the question? Sorry, we maybe cut off or got a little quiet.
Yeah, did you evaluate any sequence length limitations in the model?
You want to take it? Yeah,
sure.
So are you referring to like the length of our prediction that we're only predicting 6 hours into the future?
Correct.
Yeah, so
or in the past.
Okay, I'll talk a little bit, and Lily can probably also talk a little bit. She worked more on the LSTM. The reason we chose 6 hours was that was the optimal range we found for both managing how long it took to run the model, along with how far we're looking into the future. That also balanced how accurate the model was, and 6 hours was what we found to be the best time. Lily, do you want to say anything more to that?
Yeah, so 6 hours just kind of was the sweet spot where after 6 hours, the accuracy tended to drop off a lot. I think if we make the model more complicated, then that means that the accuracy might be high, like for a couple of hours past 6. But that also means that the model could take longer to run. So it's kind of a question of how complex we want to make it and how much like time and computation, like how inexpensive it is in order to actually run it, we want to lose. So it's kind of balancing the two.
Thank you.
Thank you.
I have a quick question from Aviation Research, Mike Paglione. Very impressive work. A lot of work went into this. You can tell from what you reported. I'm curious in the training of the model and the decision, the thresholds that you use for the weather decisions. Was that driven from operational folks, those thresholds, or was it based on the performance of the model? Did you have to kind of tweak those thresholds to get a good prediction? And was that like an interplay between setting those thresholds and then the training of the model? I'm just curious on how that all played out.
Yeah, so right now the thresholds are as is. We did think about tweaking it, and that's also talked about a little bit in our risks and mitigations, where if the model was underperforming, we could change them a little bit just to help it perform better. But right now the thresholds are as is in terms of if you kind of go online, do some research and find out when flights are actually delayed. There are like small ranges. We I believe took the maximum of them just to play on the safer end. So right now the threshold ranges are as they should be.
Okay, so you pretty much selected them from operational parameters that you got from the operational folks. Okay, that makes sense. Yep.
Yeah.
And then I guess a quick comment on the second threshold that you referenced when it came to actually choosing, right? At that point, we did do like an optimization process. It's a very easy, like one-dimensional process, right? But we said, how do we optimize over this threshold range to obtain the best accuracy, right? And so obviously you could be a little bit more conservative and drop that value like low. Like if you go to 0, you'll be predicting delays for everything, which is obviously a nebulous choice, but you could do it regardless. So given our considerations, we did the optimization process and ended at a value of around 0.2 for that threshold set.
We have just under a minute and a half for questions, so I want to go Dr. Wenke in the room, and then we have Jason Johnson and Steve. If we can move quickly, thanks.
Okay, thanks for the presentation. It's interesting to see this kind of application. And of course, weather forecasting is hugely important to how this works. I think it would be interesting to try to map this to kind of the way things happen today in terms of how we manage, weather impact. So, a flight can be delayed for weather, because there's weather at the source, at the origin airport. It also could be delayed because there's weather at the destination, right? It could be delayed because there's weather en route. And I know you're trying to score, how accurate you are based on the weather at the airports. I mean, I think it's hard to really say, my guess is you're doing better than you think in terms of flights that are actually being delayed, because some of these flights are going to be delayed for entirely other reasons. So it might be useful to try to separate that out, but also to map, the recommendations that this makes to, ground delay programs, ground stops, and the kind of mechanisms that are actually used in the system. And I think if you kind of think about it in that way, I'll bet you could modify the way this thing predicts to sort of predict when you need those things, right? And then you don't have to worry. What the advantage that might give you is that instead of having to try to reschedule each flight individually, you're throwing that to the airlines, right? You're saying, here's the rates we're going to accept, and then they can decide which ones are more important, and do sort of internal business optimization. So just some ideas. I mean, I think all of those processes that we do today would be greatly improved by better forecasting of when we're actually going to have the constraint.
I think just to follow up on your point, because you bring up something that we were touching on, but unfortunately didn't have time to do, was to talk about a little bit of the entropy of our output, in the sense that, right, like you produce a schedule, right, and you want it to not be the case that you produce a schedule, within one time span, and then like 30 minutes later you produce a wildly different schedule, right? So there is these concerns of like handling the entropy, so to say, between the schedules, right? So that you have something that people can actionably do something on, right? You don't want to have operators attempt to accommodate one schedule and then change everything to accommodate another one, right? So those are the type of things that also fall into our future work that we're looking at. But yeah, those are considerations that, from in practice approach that we try to keep in mind when we're doing this.
Okay, I'll keep my question very, 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 very brief. The buffer window that you talked about, Are you planning on checking that over time? Because I really like this project and I was reading through it, and that was my really only question and kind of going back and forth is to figure out if that's going to be evaluated. Because what was brought up earlier about all the airports, right? So that buffer is going to grow, and if you have a way to evaluate that buffer, then you can adjust based on weather in certain situations. Have you thought about that part?
Yeah, so one thing we considered doing with this model was incorporating like trying to minimize what the buffer times are into the actual like LSTM and like that process. We ended up not doing this, but this is something that the model like can be like reworked to work in. It's to like try to minimize these buffer times within like the actual prediction process.
Yeah, and then
Awesome.
just to follow up on that, there's like two types that you could do to your point, right? You have this idea of like, can you choose an optimal static buffer, right, across across, I guess, airport management, but also to your point, right, could you also do an adaptive dynamic buffer, right, that you have adaptively setting? So those are some of the things that we played around with. I think currently we ended off on doing static buffers and evaluating that, though we never were fully able to incorporate it. But you know, the obvious evolution to that would be to have those more of a dynamic properties that would also help efficiency through the airport. So yeah, those are really good questions that lead into kind of where we want it to go. So thank you for your question. Appreciate it.
Awesome. Good job, guys.
All right, next up, we have Embry-Riddle Aeronautical University with SkyTwin, a digital twin of the NAS for air traffic.
Okay. Thank you, Jamie. My name is Alex Davidoff.
My name is Luke Newcomb.
And I'm Sarah Reynolds. And our project was inspired by the concept of trajectory-based operations, or TBO. Now, TBO is a really transformative technology that allows you to plan your flights using 4D trajectories rather than the traditional waypoint system. This amount of flexibility and choice can improve aircraft performance, lower the environmental impacts of aviation, and help airliners avoid weather delays and other impacts. Why aren't we using this already? Well, one main consideration is that it's a very complex system in terms of data. And one of the consequences is that complexity could actually overload the workload of our air traffic controllers, which is not something we want to do, especially during times when we're facing controller shortages. So when we came up with our solution, we knew that we needed to meet the expectations of TBO while allowing for growth in the airspace use in the future. And we wanted to rely on automation and machine learning to help reduce that burden on our air traffic controllers, all while maintaining the FAA's safety standards. Enter SkyTwin. We chose a digital twin because it allows us to not only monitor our data in real time, but it allows us to see how our decisions impact the near and far future of the NAS. So come with me as we take a look at what SkyTwin can do. Not only can we monitor our aircraft in real time, but through the use of our ML prediction models, we can view the future status of aircraft, which allows us to identify potential separation violations before they happen. We also have the ability to use TBO to optimize our flight plans. So today we'll be talking to you about how SkyTwin, a digital twin of the NAS, can manage flights in accordance with TBO, optimize goals such as efficiency and environmental impact, while adhering to the rigorous safety standards that the FAA has put in place. Luke is going to start us off by talking about our trajectory prediction model.
Thank you for the introduction, Sarah. I will be talking about the first component of our SkyTwin system, trajectory prediction. The current waypoint-based flight plan system does well to allow air traffic controllers to manage the airspace in discrete areas. Airspaces can contain a set of waypoints that can direct traffic. However, TBO is going to need more granularity than these waypoint-based flight plans can provide. It's going to need the locations of each aircraft at any given time in order to form those trajectories. The purpose of the trajectory prediction model is to convert existing waypoint-based flight plans into trajectories for use with the rest of the system. This would allow for a period of transition to TBO, where some flights may still be using a waypoint-based system. Here's a graphical representation of what I just discussed. On the left is a waypoint-based flight plan consisting of a path through a series of waypoints from one airport to another. On the right is a trajectory-based flight plan consisting of a series of points at specific times. It still follows the waypoint-based flight plan. However, it's in a form that the rest of the system can use. In order to accomplish this, we used a wavelet-based trajectory prediction model. I'll first talk about why we chose such a model. So here's a graph showing the components of an aircraft's trajectory over time. We can see that something like the speed of the aircraft, shown in red at the top, is high frequency information. It changes rapidly. While something like the altitude or latitude of the aircraft changes slowly over time or is low frequency. The model needs to be able to understand both high and low frequency information. After reading many papers in the area of trajectory prediction, we settled on a wavelet-based approach as it showed the most promise. This is also supported by the larger study of the application of wavelet transforms. Here's an example high-frequency input signal. This could be provided directly to the model in order to predict the path of aircraft. However, it's more difficult for the model to understand such a volatile input. Instead, we use a wavelet transform, similar to a Fourier transform, which converts the time-based input signal into a frequency spectrum. A wavelet transform can be thought of as sliding a small wave or wavelet across the input signal and recording how well it matches the input signal shape. This frequency spectrum consists of how much each frequency is present in the signal at the current time. This can be provided to the ML model instead, as it doesn't change as rapidly, and it allows the model to more effectively learn the patterns of aircraft maneuvers. Here is how the trajectory prediction model fits in with the rest of the system. So the input to the model is the waypoint-based flight plan, as well as the previously predicted points in the trajectory. This is provided to the ML model, and the ML model generates new wavelet coefficients that correspond to the new point in the trajectory. This new point can then be added to the previously predicted points and the process repeated until the aircraft reaches its destination. In the end, the model was able to predict flight trajectories. The performance of the model could be improved though, as it seemed to have problems generalizing to the entire US airspace. Previous work in this area did show better accuracy when the model was constrained to just predicting in a localized region, such as around a specific airport. However, we believe that scaling to use more training data would improve the performance of the model. As you can see on the image on the right, the path of real historical trajectories, which the output of the model is based off of, do not always follow waypoints exactly. So this data could be processed to also improve the accuracy of the model. Additionally, there are many different kinds of wavelet transforms that could be experimented with in the future in order to improve the results. The results of the model would need to be improved in order for this to be used in a real production environment. And now Alex will talk about the second component of the SkyTwin system.
Thank you, Luke. Now that we've talked about trajectory prediction, and before we go on to our other ML component, flight optimization, it's important to discuss the safety of our solution. Safety within trajectory-based operations is paramount, especially when machine learning is involved. Machine learning models are inherently black box, which makes ensuring their safety both challenging yet necessary. Also, converting flight plans into trajectories increases the risk of conflicts, as the current waypoint-based system already has mitigations in place in order to avoid such conflicts. Therefore, our solution must maintain the safety of the national airspace system as it transitions to new efficient frameworks, such as trajectory-based operations, while supporting ML usage. This brings us to our solution, a novel conflict detection algorithm for detecting separation violations between aircraft. We employ a grid-based method over the continental US to predict potential conflicts in advance. On the right, we have a visualization of what a sample grid square might look like, containing a small portion of the airspace that aircraft may share. The conflicts are checked within the grid square as well as within surrounding grid squares. It's important to note that our flight plans are defined by trajectories, and trajectories consist of a series of trajectory points, which have latitude, longitude, altitude, and timestamp information. Our conflict criteria is threefold. For two aircraft to be in conflict with one another, they must meet the following criteria: a vertical separation of less than 1,000 feet, a lateral separation of less than 5 nautical miles, and both of these must occur within 3 seconds. Additionally, our trajectory points are spaced 2 minutes apart, so you might be wondering, how can we tell what happens between the trajectories? Well, our algorithm detects if 2 points between 2 different aircrafts are possibly in conflict. And if they are, the additional fine-grained points are interpolated every second. So this can be seen by the figure on the right, where we have 2 pairs of points belonging to 2 different aircraft, and these points are possibly conflicting. So the algorithm interpolates these fine-grained points every second, and then the conflicts are actually checked within these interpolated points. Now let's see our conflict detection algorithm in action. So here we have the US grid overlaid, the airspace grid overlaid over a map of the United States. Each grid square is 0.5 degrees latitude by 0.5 degrees longitude. And also we have 200 sampled flights from the NASA Sherlock database. If we remove that map overlay, we can see these flights more clearly, and we can also see that a conflict was actually detected in Southern California. Now, zooming into this conflict a little bit closer, and by also visually inspecting the 2 points, we can see that it is indeed possible for a conflict to occur here. These points occur at approximately the same time in approximately the same location, and they belong to 2 different aircraft. Now, zooming in even further, we can see where this conflict likely occurs at a point where the 2 trajectories appear to meet. Now, as demonstrated, our conflict detection algorithm successfully detects conflicts, and it does so quickly. Our solution is highly scalable at O of n log n complexity, as opposed to traditional pairwise conflict detection algorithms of O of n squared. These results are very exciting, and complexity-wise, our algorithm performs as highly as an algorithm of this scale can be expected to perform. On the right, we have a figure demonstrating the performance of our system, and this was obtained by pressure testing our system on an increasing number of flights. Our solution is suitable for centralized execution with minimal adaptation, such as converting to a compiled programming language or multi-threading, and can alternately be distributed across various airspace sectors rather than be centrally executed. Now I'll pass it on to Sarah to talk about flight optimization.
Thank you, Alex. So one of the really exciting things about working with TBO is that we can actually try to optimize the trajectories of aircraft. We have a lot of potential in this domain. So not only do we want to avoid conflicts with flights and potential weather patterns, but we want to reduce fuel usage to reduce the environmental impact of our aviation sector. And we want to reduce time in flight because that is a business concern that passengers rely on. But we can expand this to more complex concerns, such as avoiding contrails. Contrails are one of the biggest polluters in aviation, you are able to avoid them by avoiding flying through certain weather patterns. So to do this, we developed a reinforcement learning model. This is a deep neural network in which airplanes act as agents within a simulated environment that represents the NAS. Our airplanes are able to take actions in the environment. And in return, the environment updates itself and produces a reward that sort of determines how good the action the airplane was. And through this reward system, the airplanes are able to learn appropriate actions as they move from their starting point to their destination. Let's take a little bit of a deeper look at this deep neural network. So as input to the neural network, we put in the current position of the aircraft and its goal, and the state of the environment containing all sorts of information about the NAS. A lot of complex calculations occur, and then the model is able to output the heading, speed, and altitude changes that the aircraft should make in the next time step. This action is added to the environment and rewards are calculated. The rewards propagate back through the system using proximal policy optimization, which is an ideal optimization strategy for reinforcement learning of this type when you have multiple agents interacting in the environment at the same time and you have a highly complex environment. Now, I've talked a lot about rewards. What does that mean when I'm rewarding the aircraft? And we have a couple of different calculations. One is fuel usage. We estimated this using a drag estimation equation based on the altitude and thrust of the aircraft, obviously going for lower fuel usage and rewarding that within the system. Now, there are much better models out there. Unfortunately, airlines keep them very close to their chest. They are proprietary, but that is something that could easily be switched out to improve the performance of the model. We used our own conflict detection module to harshly punish aircraft for breaking separation rules. Additionally, we prioritized efficiency. We wanted to ensure that we spent as little time in flight as possible, and we encouraged directness by calculating whether they were heading directly towards their goal airport or whether they were taking a more superfluous route. My favorite thing about the training function or the reward function is the modularity. Once this model has been trained, you can actually change the reward function to increase the complexity or to optimize for other features. And what that allows is it allows it to take what it has already learned and continue advancing to meet the optimization that we require. So you can see a result of what it's able to calculate on the right of the screen here. So initial training leads the aircraft to the goal effectively. As more objectives are optimized, the training becomes more extensive and more expensive. That is the one downside of reinforcement learning, is that there is actually a very large upfront training cost that needs to be invested in. On the other hand, once you have your reinforcement learning model trained effectively, it is very quick to implement and it can handle a lot of predictions at the same time, and therefore would result in a large reward in the SkyTwin system. Today, we've talked to you about how SkyTwin can ease the transition for the FAA from waypoints to TBO, how we can use automated analysis and machine learning to help focus air traffic controllers' attention, and finally, how we can optimize flight trajectories for more efficiency in the NAS, allowing the NAS and aviation to expand throughout the coming decades. All the while keeping in mind the rigorous FAA safety standards that keep our skies safe. Thank you so much. We're ready to answer any questions while you enjoy this lovely visualization of the reinforcement learning training process.
So first of all, Daytona or Prescott?
We're the Daytona campus.
All right, good answer. Plus, you said your model has challenges, I'll say nationally, right? Or there was just challenges in trying to predict this across long distances?
Mm-hmm.
Okay. So when I hear that, and when I think about the future, and maybe you thought about this, I might consider pivoting this into advanced air mobility and more regionally based.
Mm-hmm.
How could this be applied in the LA Metro, New York Metro, DC Metro, right? Those kinds of areas where you have, how would we incorporate, say, Amazon drone deliveries, Uber Air, and commercial aircraft plus GA? So to me, instead of maybe going nationally at commercial airspace, consider pivoting into regional with the advancements of additional air assets in the NAS.
Mm-hmm. Yeah, I think that's absolutely a wonderful idea. And the way we structured the development of this, you can change the parameters of your aircraft model. Currently, because we were limited in time and resources, we limited to a commercial airliner, but you can actually change the movement abilities, and through that, you're able to adapt to not only other planes, but other types of UAVs and such. And I think that's a great idea.
Online, Mike?
Yes, thanks. Very impressive work. This is an area that we've studied a lot. There's quite a bit of automation in the en route centers that support the en route controllers, as well as in the terminal area, with another set of tools that support them, and do alert them to conflicts in the future. And then the air traffic controller has the job to utilize that information and then communicate to the pilot and make the recommended clearances to make sure they don't have a conflict in the future. So I'm curious, you talked about two things. You talked about helping the air traffic controller with that problem, because as we know, traffic keeps increasing, and with AAM and other things, it's going to get even harder. So exactly how is the tool, that the digital twin that you are proposing here, how would it help the air traffic controller in that function? And then, or is it more focused on the airline ahead of time in optimizing their flight plan that they submit into the system? So how is it integrated with the decision makers in the system today?
Yeah, absolutely. So we considered multiple stakeholders when we were designing and developing this product. From the airliner's perspective, their operations centers, if you're able to see potential separation violations when you're doing your flight planning and you're able to make the adjustments at that point, that can help reduce air traffic controller burden, because there are fewer separation violations. In addition, in the actual, in the centers and in the towers, you're able to be alerted, in addition to the existing technology of potential conflicts, to help focus attention on areas that might need the extra bit of focus and a bit of help, if that makes sense. So we were really trying to make a system that's beneficial to all of the stakeholders in the FAA.
And then one thing to note is that our system is specifically tailored towards trajectory-based operations. So we wanted to try to decrease the burden on the FAA and other laboratories when transitioning to this new system. So that was another main motivation for the conflict detection. It's not necessarily only for what we have right now, but it's also for future frameworks as well.
Yeah, this is Gabe. I have a question. Do you have you thought about? It wasn't clear what kind of. I get it as a flight planning tool. Like I understand that use case, but as a real-time tool, what information are you taking in to help you, emulate what's happening in the real world?
Right. So so conceptually, in terms of real time, obviously this is not currently working in real time, but what we have is the ability to integrate with the FAA's SWIM data flow, so you can get these accurate position updates. We really spent a lot of time considering the real-time data flow of this system. And while it might not be potential to implement today, the ADS-B data flows and the various tracking that is going on is something that could contribute to this more centralized system. I'm very fascinated by the use of ADS-B data and the potentials for encryption and avoidance of adversarial attacks via spoofing. So that's something we've talked about a lot in terms of the development of the system.
Yeah, and a quick note of advice, you should also think about the information available on board the aircraft and the flight management system. Because, in situ up in the air, the aircraft knows the real conditions, which are going to be more accurate than your forecast.
Yeah, we read a really fascinating trajectory prediction paper that showed that if through a network of communication of the aircraft, getting the real-time weather data in the sky, that actually improves trajectory prediction and could improve a digital twin such as this, even further reducing the error and increasing its effectiveness.
All right, we have time for one more question, so we'll take it from Steve online.
Yep, thank you. So just a quick question. So appreciate your use of reinforcement learning for your model. And I know it's supposed to be a quick question, so I don't want to elaborate into a whole nother presentation, but if you could describe the architecture to that model just a little bit more in depth, like was it just a typical recurrent neural network, or what exactly model architecture did you use? And then along with that, what accuracy and precision scores did you find your training data against real world data when you did your comparison?
Okay, so in one, to answer your first question, the environment was handled through a 3D CNN. All of the other aircraft information, such as their goal, their current location, and their current heading speed and altitude parameters, were all linear vectors, and then those were combined into LSTM. No, we did, I think they were RNN layers, and they used ReLU activations, which we found to be mostly effective. And we didn't have a real world baseline, right? Because we're calculating these optimizations and we have these approximations of fuel usage, but real evaluations of time. And currently, so as we said, there's large upfront training. And one of the downsides of that is we have, as we were learning the reward structure, we can effectively guide to the model, and we were able to reduce, I don't have the exact numbers right here, but we were able to reduce, because they occurred after the submission of the paper. But we were able to reduce time in air, and we were able to reduce fuel usage based on our estimations. But we also need to further expand this model to get the most accurate numbers, if that makes sense.
Great, thank you.
Thank you.
So much. All right, next up is Texas A&M University with reducing aviation emissions with MILP optimization. And after that, we'll take a quick break. Yep, make sure it's on.
Test.
Testing.
Sweet. Good morning, everyone, or as we'd say in Texas, howdy, everyone. My name is Harsh Gangaramani. I'm an undergrad computer science student at Texas A&M. I'm joined with my friend and colleague, Akshat Kumar, who is a Master's of Aerospace Engineering student at Texas A&M. Advisor, Dr. Benedict, could unfortunately not be here today, but regardless, we're super excited to talk about our research on how we want to contribute to sustainable aviation by reducing emissions using optimized flight networks. Before I get into the presentation, I would seriously like to express my gratitude to these advisors from various entities. Without their help, we would not be where we are today, and they've been a great help. So let's get straight into the problem. Since the year 2000, aviation emissions have been increasing rapidly and have seen an unprecedented surge post-COVID due to the travel boom. If things keep going the way they are right now, estimates show that emissions could more than double in the next 25 years, which is not good. In addition, there have been mandates across the world which make airlines want to go net zero by the year as early as 2040. Such mandates are the US Aviation Climate Pact, as well as the EU Green Deal. Again, these mandate airlines to go net zero by 2040, but the projections show that it is not estimated to meet that. So how can we prevent emissions from aviation to increase exponentially over the next 25 years? Well, let's look at how the industry is addressing this problem right now. So I'm sure if you've been on the news lately, you've heard about sustainable aviation fuel. What SAF is, it's very similar to traditional aviation fuel. It burns the same amount of carbon, except it has a lot less carbon intensive process. And it does show very promising results. And that's why airlines have made mandated as well as voluntary commitments to adopt this by the year 2030. However, projections from McKinsey show that while there is a lot of demand for this fuel, supply for this fuel could shortfall of demand by the year 2030, which would make its implementation hard. In addition, there's also a lot of ongoing research on electric and hydrogen aircraft as a means to travel with less emissions. Again, just like sustainable aviation fuel, these show great results, and we as humanity should keep developing these to make sure they're implemented in the future. However, they are still very early stages, and as of right now, they will not be developed fast enough to meet our sustainability targets. And to meet those, we need to take action right now. And to discover more about this issue, we started talking about the parties involved, the airlines. We developed a very meaningful relationship with operations managers at Southwest Airlines, such as Jamie pictured over here. And while talking to them, we realized that while airlines are very committed to sustainability, in the end, their end goal is to operate as a business, which means prioritizing revenue and meeting financial targets. Also, for later, this operations relationship with Southwest gave us a compelling reason to use their data as a baseline for our research, which makes sure that our research is practically applicable. More on that later. But these talks made us rethink the problem. Rather than reducing emissions as much as we can, the problem is really to find the balance between reducing emissions while meeting financial targets, all with a solution that is practically applicable.
So let's talk about our solution. We created one of the first mixed integer linear programs that minimizes emissions across the entire well-to-wake jet fuel spectrum while still meeting financial targets and incorporating realistic operational constraints. Before we jumped into the solution, we did a lot of research into other research and quickly realized that while minimizing emissions in the aviation industry is not a new topic, a lot of people have done it. They focus mainly on the flight operations. Obviously, that's a major component of the emissions released by the aviation industry, but it's not the only component. That's why we also looked at ground operations and the jet fuel supply chain. And while getting data for flight operations is relatively easy, finding data for ground operations and the jet fuel supply chain is a lot harder, and it took a lot of work. And so we'll talk about the data sources really quickly. First, for flight operations, we use the Bureau of Transportation Statistics T100 segment database to get historical data for entire flight networks in 2023, specifically the Southwest Airlines flight network. A major assumption that airlines make is that historical data reflects current and future operations, and that's an assumption that we made as well. Then we use the OpenAP aircraft database to model emissions factors for different aircraft and engine combinations. This physics-based, extremely accurate estimation model gives us the emissions for any aircraft, specifically in the Southwest Airlines fleet, at various altitudes and for various performance characteristics. Then, to get revenue data, we use the BTS's market database to get average fare price for each route in the Southwest network. And then finally, for flight operations, we use the FAA's airport data portal to get things like altitude and runway lengths to see performance at various airports across the network. So again, these were relatively simple to find online, but getting ground operations data was a lot harder. We could not find anything that gave us the information that we needed. So we tried a little bit harder and ended up using our connections at the Texas A&M Transportation Institute, or TTI, to get access to their airport emissions inventory, which is an extremely robust document that gives emissions factors for basically any ground operations vehicle you could think of at airports of various sizes across Texas. And given that Texas is the second biggest state in the US, we have airports ranging from DFW to the smallest little regional field. We were able to extrapolate this data to airports across the country. And then we did a similar thing for the Airlines for America jet fuel emissions report for the jet fuel supply chain. To incorporate all this data, we tried a bunch of different analytics methodologies. But in the end, we used a methodology that's quite old, but still quite effective, a mixed integer linear program, or MILP for short. And I won't go into the complex math behind what makes MILP work. However, just know that it is ideal for optimizing aviation networks because it allows us to model these networks as graph networks and allows us to incorporate the supply and demand dynamics along with realistic constraints. For example, minimizing the number of flights to the number of aircraft currently at an airport, which again reflects real life as much as possible. And from this, we were able to output an optimized network and a number of results that are pertinent to our presentation. And so first, I'll talk about the emissions results from our optimized network. So first, look at the column called the actual network. That data you see there is from the official Southwest Airlines One report for 2023, such as emissions, flights operated, all these were what actually happened in 2023 for Southwest Airlines. Then the next column over is our optimized network. We were able to see anywhere from a 5.1 to 18.6% reduction in total amount of emissions, depending on the type of methodology we used, while still meeting passenger demand. This was primarily done by reducing the number of flights operated, making the other flights more efficient, right? And that's something that we've experienced ourselves. Just a couple of weeks ago, we were taking a flight home on a 737 MAX 8, a huge 175 passenger plane, but there was only 30 people on the flight, right? It's producing an incredible amount of emissions while not necessarily meeting financial goals. And so that brings us to our financial results. We were able to generate a Pareto curve between emissions and revenue, giving airline operations managers a quantifiable view of their trade-off between financial feasibility and their sustainability targets. We were able to find about for every $1 of revenue that is lost, 1 kilogram of CO2 is saved. We also created this interactive map that shows that with changes in revenue reduction, which airports across the US are most effective. Again, giving operations managers a clear, simple visual view of how their emissions goals can affect different airports in different regions across the country. And as you can see here, the graph network is pretty obvious in how we implemented it. And then finally, we were able to find the ideal redistribution of Southwest Airlines aircraft across the entire network. Southwest has 3 different types of aircraft, the 737-700, 800, and MAX 8, each with their own characteristics. And we were trying to find which airports and which regions of the US would most benefit by having these aircraft flying their routes. So first, for the most least efficient, I should say, 737-700, unsurprisingly, we found that it should be reduced on most major routes while being increased into other routes, especially at smaller airports. Then for the next most efficient, the 737-800, we found that, again, unsurprisingly, it should be increased at mid-sized airports, especially in the Western and Southeastern United States. While finally, for the highly efficient MAX 8, it should be increased at most hub airports across the country. And these results are pretty intuitive, which first of all lends credence to the accuracy of our model. However, what we were able to show is the exact airports and exact regions that airports can make the biggest difference in how they think about their flight methodologies. This could be used not only as a quantitative solution, but more importantly, as a qualitative solution. As airlines have a lot of factors to think about, this can be used as a general methodology impact. Of course, there's still much work to be done. We love to incorporate many more characteristics into the emissions model, such as contrails. Also, things like flight disruptions due to weather and airport slot management, which could ultimately increase emissions significantly, depending on how much time those reroutes have to take. And finally, there's an ever-changing landscape in the policy and industry for the aviation industry. And we love to incorporate things like carbon credits and, as Harsh mentioned, SAF into how it will affect how airlines think about their emissions goals. So in our study, we were able to show that airline efficiency optimization is a viable and immediate way in which we can start reducing emissions in the aviation industry. We're able to show up to an 18.6% reduction in emissions with little to no infrastructure changes. And we found that while there's still much work to be done into creating a model that is realistic and able to be implemented, that this is a great first step into an aviation industry with a net zero future. Thank you.
Let me ask a question.
Sure.
So I like your future work. You've got a lot of interesting considerations in there. There's a couple of others I think you might want to think about. I mean, one of the things about, operating the same or servicing the demand with lower frequency does actually link to demand, right? Because the demand or the frequency offered is actually one of the things that entices people to fly a particular airline. So, I mean, I'm sure the airline themselves have models for what frequencies they need, and there might be a way to couple that in and make that trade-off, right? So you might want to operate a flight maybe that's only 80% full, just because it'll pull in more, passengers, and that might change your constraints a little bit. And also the notion, you want your load factors as high as possible, but as has been demonstrated actually fairly recently by Southwest themselves, I want to say a year or so ago, if you fill all your airplanes and you have to cancel a flight or two, that becomes a problem. So there's a resilience, robustness kind of consideration that might actually, again, it might be an analytical way to capture that within the mill that you could get into, and I think that might be of real interest to the airlines from operations perspectives. But thank you, very interesting work.
Great, thank you.
If I could real quick, so I know during your presentation you said you weren't planning on elaborate on the mathematical implementations that you did, but on the other hand, mixed integer variable optimization is like a broad categorical approach of which you can do lots of things. So could you elaborate at least a little bit on any specific implementation you did mathematically for your model to generate the results that you found?
Sure. Yeah, that's great. And that's a fantastic question. So specifically, like I mentioned, we use the mixed integer linear program, which is, like you said, a very broad class of optimization algorithms. So specifically, there's kind of three main components to it, right? There's the objective function, which is what you're actually trying to optimize for. There's the constraints, which we kind of alluded to. And then there's your decision variable, right? Which is what actually changes, what your algorithm can actually change to make the results different, right? And so for us, the objective function, which, as you can probably tell from our slide here, is reducing emissions, minimizing emissions as much as possible. And our decision variable, which may or may not have been clear in our presentation, was the distribution of various aircraft. Again, there's 3 different types of aircraft in the Southwest Airlines network across different airports and different routes, right? So that's an integer variable. You can't say that half an aircraft is flying from here to there. At least, not right now, how airlines fly or airplanes fly. And so that was ultimately what we were trying to change, the distribution of different aircraft. And like Dr. Wenke mentioned, the kind of the load factors and things like that. And then some of the constraints, like I mentioned, there's an airport capacity constraint, which says you can only have a certain number of aircraft at your airport at a given time. And thus that impacts how many routes you can fly from that airport at a given time. As well, we included constraints like demand, right? Depending on historical demand, again, like Dr. Wenke mentioned, Southwest Airlines might not be willing to give up a market, right? Even though they only have 30 people on their flight. And so things like that, we looked at the historical demand from the BTS T100 database to incorporate constraints like that, and as well as some other assumptions that I won't go into right now. But thank you for the question.
Thank you.
So I have not seen the detailed formulation. Did you construct a fleet assignment model?
Sorry, could you speak the question into the microphone so that the folks online can hear it as well?
Anyway, maybe I'm getting old, Craig. No, so the question is, assuming that you fundamentally implemented a fleet assignment model.
Sure.
Did you enforce the balance constraints at each fleet type, sub-fleet type?
Do you mind explaining more?
Okay, so a fleet assignment model is a model that we solve in the airline industry.
Sure.
To determine which size aircraft to assign to which route.
Sure.
And so each model or sub-model, a fleet or sub-fleet, you have to enforce balance constraints to make sure that every node at every airport, the number of that type coming in is the same number of that type going out.
Yes. Okay. Yeah.
Right. So the metric that we use is what we call spill, which is how much of the unmet demand there is, right? So wouldn't the actual objective of reducing spill automatically take care of emissions per passenger? Because you're really trying in the fleet assignment model to match the aircraft size to the demand on that leg, considering also the fact that you may actually have to fly a leg with slightly less load factor because the following leg that aircraft is going to fly. So in my copious spare time, I'm chairman of the board of an airline in the Cayman Islands. And we actually fly airplanes sometimes half empty because the leg could have a huge, distribution imbalance in terms of direction, flow imbalance. So I'm just trying to understand how your model is different from a fleet assignment model, because it seemed to me that a modifier tweak that itself would cover it, but a slight modification would also cover it.
Sure. Yeah, that's a fantastic question, and thank you for explaining those. I've never heard of spill, but I mean, it makes sense. So I think what we kind of were able to gather from our conversations with Southwest Airlines and some other stakeholders is that, ultimately, of course, airlines are trying to reduce costs as much as possible, right? And fuel is a part of that, right? Which directly correlates to emissions. And so, of course, airlines are always indirectly reducing emissions, such as, the ways in which you talked about as well. But I think what we were trying to do that was a little bit different is that as of right now, again, airlines kind of keep a very closed and shut, idea on how their models actually work, right? That's proprietary. So we don't know exactly what they're optimizing for, but generally what we got from them is that they're looking for demand, they're looking for revenue, they're looking for all these different balance constraints, and that emissions is not directly being optimized, whereas our model is that we're directly trying to optimize for the emissions, right? Which gives up some of these other constraints like you're talking about, which increase operational in real life, right? Airlines need all these different operational constraints that unfortunately we didn't take into account for this model, given the amount of time and resources we had, and how much knowledge we have about the airline industry as students. But I'm sure, in the future, as we start incorporating some of these models, it might become easier to start implementing things like balance constraints, things like, making it more similar to a fleet assignment while still keeping emissions as the ultimate goal of this, whereas emissions is almost a byproduct, right, of other optimization methodologies. Thank you. Perfect. Thank you so much.
Thank you.
We are ready to start back up. So next up is the University of Texas at Austin, AI-driven pilot ATC communications of airport risk.
Hello, good morning, everyone. The presentation title is From Voice to Safety, which we use a language AI-powered pilot ATC communication understanding for airport surface movement collision risk assessment. And my name is Yu Tianpeng, and I'm one of the team member. And this is Andrew, who is another team member. And we have two more team members who are not here today. And JP Clark is our faculty advisor. So the motivation of this entire research dated back in January of last year, which a tragedy happened in Haneda Airport in Tokyo, Japan, where two aircraft collided on the runway due to a runway incursion accident. And there was one Japanese Coastal Guard airplane who was given the order to hold at a certain spot called C5, but he misunderstood the command, so he proceeded to the runway where there's another A350 is preparing to landing and it's in the final approach. So this human factor error leads to the tragedy happened at Haneda and took 5 out of the 6 crew members' life. And this is a view, like geospatial view of the accident happened. And we look into the transcript post-process and released by the authority of Japanese government. And we look into the transcript, and it looks like on the highlighted area, the Tokyo Tower has already given the order to say you need to proceed to C5 and holding point C1 and holding point C5. But the JA722A, who misunderstood the command, thinks he's ready to take off with the first order, so he proceed to the runway after the C5, and that leads to the tragedy of this accident. So let's look at how about in the US. I mean, so this figure is trying to show like there are over 30 major both commercial airline incidents and accidents happened from the first 6 weeks of the 2025, which we took the data from the FAA, some statement on aviation accident and incidents. And this includes 4 major crashes for US airliners, which took 85 persons' lives. This is especially severe if we consider like the last accident that took fatalities involving US airliners was dated back in 2009. And so there are 2 basic components for safety, like risk assessment. The first one is on the mid-air risk assessment, and the second one is on the surface operations. And for this work, we are mostly interested in surface operations, where both runway issues and taxiway issues are considered. So this is the overview of this work. So in this work, we introduce an integrated framework that leverage the language AI power, so we can understand the intent given by the ATC and the pilot communications, so we can build the path planning based on the learned intent, and we can enhance the collision risk assessment during the surface movements. And our approach, we use a novel heuristic rule enhanced named entity recognition technique, which is a specific type of thing called in NLP, with a probabilistic risk modeling based on the node link graph we obtained from NASA FACET. And we use some specific log normal formulation to build this risk assessment model. And we validated this methodology with 2 case studies happened both in 2024, which is the previous runway incursion accident happened in January at Haneda, and another taxiway collision happened in September at Atlanta International Airport. And our work highlights several things. So we provide a general way to create and annotate the pilot ATC communication voice data for natural language processing techniques, because most of the data available these days for research, they are not openly available, or they just need a paid prescription. And secondly, we propose a hybrid rule-based learning model, which use a domain-specific domain-specific rules proposed or regulated by the FAA, so we can improve the recognition capability and performance of those key entities from the communication transcripts. And third is we model the surface movement with some log normal distribution and employ a node link graph structure, so we can estimate the spatial temporal collision probabilities in near real time. And on the fourth one, we validated the log normal link travel speed assumptions by conducting several parameter studies and data analysis based on the real world ASDX ground movement data. And on the last, we built a simulation to simulate these 2 accidents and visualize the risk in real time. And this is a methodology overview. So the figure on the right is basically a flow chart showing the entire process we do from voice to safety measurement. So on the beginning, we start from some data collection effort. So we collect the data from either a textual report or scanned document published by NTSB, or we obtain some MP3 files from liveatc.net, and we process them by either Tether optical characteristic recognition technique, which is a standard industry standard these days, to convert the image, which is a scanned document, to text. Or we use some speech-to-text engine, such as OpenAI's Whisper, which is another state-of-the-art in the industry standard, to process them into some textual formatted data. And then we use another open source tool to convert this thing and to annotate the data by ourselves. In this effort, we are mostly interested in the flight cosines and the aircraft state and the destination. And then we use some natural language processing tool called Spacey, which is another open source tool. And we proposed an idea of doing fine tuning based on foundation models with some ATC rule enhancement and override. So we use either augmented training to augment these rules into the training data, or we post override the prediction results from the machine learning model based on the rules. So after this, we get the cosines for the aircraft and the destination intent for this specific aircraft. And then we can generate the path, which is called the intended taxi plan. And based on this path, we calculate, we can do conflict detection, we can do compliance check, just based on the machine learning results. And in this specific part, we focus on doing collision risk assessment. So we propose a spatial temporal formulation to do this conflict detection, which Andrew will talk about the formulation later. So for the second part, our taxi plans are generated based on a similarity search approach, which is basically we do some similarity search of learned entities and airport node from the NASA FAA data format and based on the embeddings. And notably, we validated the link travel speed parameters through the real-world ASDX flight data, which we will also show later. So for the ATC rule enhancement, what does that mean? So that means we refer to several FAA documents. For example, FAA document 77110.65 for the standard physiology and terminology used in air traffic control, such as Alpha, Beta, Charlie for ABC. And we also refer to FAA Order 7340.2N for the standard phase contractions. For example, the figure on the left, there's a cosine called Speedbird, which is basically the contraction of British Airways. And the figure on the right, so for these rules, it's basically just a big dictionary format, and we can keep expanding these rules to be more inclusive. So it's pretty flexible for any real-world engineering implementations. And on the figure on the right is a table showing the machine learning results by extracting the keywords from the communication transcripts. So we're showing the simulation results from the Atlanta taxiway collision incident. Basically, we are showing what is your cosine and what's your current state. You are taxiing or you are continuing holding or doing what? And what's your destination runway? And based on the destination runway, we can get your destination node or intended node because that's the entry point of that specific runway. And we can also do other type of similarities. For example, what is Echo? For example, what is Romeo from the airport node link map? Go ahead.
Okay. Hi. So once we have this taxiway plan and basically have a set of waypoints on the taxiway that several aircraft will be taking to get to their destinations, we can start trying to analyze whether this will result in an accident or not. So the accident we're defining is basically that the two aircraft occupy the same area of the taxiways at the same time, and we use some characteristic radius relative to like their wingspans. So that there's, for a general formulation of this, you might have to use Monte Carlo sampling and some rare event estimation techniques to try to estimate this probability. We're going to make a few assumptions so that we can actually turn it into a nice analytical problem that's easy to compute. So we are concerned in this problem with collisions that happen at the nodes of where taxiways meet and intersect. And we can build a model just by learning distributions of the time it takes to traverse from one node to another. So you have this travel time, gamma k, for some aircraft moving along taxiway links from one point in the start of their taxiway plan to a potential point of collision. And the parameter that we actually learn from the data is the velocity or the speed along each taxiway link. We'll show that you can model it quite well as a log normal, and the log normal has good properties for inverting this so that you can turn velocity and target distance into time. So you have a nice analytical solution. So we sum these log normals together and convolve them using a Fenton-Wilkinson approximation. And Then we compute this this overlap between the distributions of two aircraft at a potential node where a collision may occur. So yeah, we compute the probability of this collision as when one aircraft reaches a node, what's the probability that the other aircraft is within this collision radius, and then extend this to the probability that this happens at any time during the operations of these two aircraft. So learning the parameters that go into this, we use our other side of data that isn't the voice to text side. We use a mix of ASDX data from the Sherlock data warehouse, which gives us the ground movements. And we look at this for ATL. Then this map of ATL that we have, a node and link graph, is from the NASA FACET database. And they also have one for Tokyo, Haneda, which is quite useful for the other problem. And when we don't have information for a particular taxiway segment, we use Advisory Circular 150-5313B, which is advisory on the design of airports, and it has distributions for expected taxiway speeds depending on the type of taxiway. And we fit these distributions for 2 days at ATL, and they line up with log normal quite well, better than a normal. So we can go ahead and use these learned distributions in our risk assessment and model. So here we have the Tokyo Haneda runway incursion. So this was January 2nd last year. An A350 that was landing struck a -8 that had misunderstood communications and had gone from its hold point into the runway. So in the left, we have a reconstructed version of the accident, if you can see it again, where they do collide at the on the runway after it goes past this hold point. And on the other side, we have an overlay of the collision risk that we've computed at the nodes and interpolated in between nodes. Sure enough, as our methodology worked out, and we actually have a high probability of collisions at the node where the collision actually occurred on runway 34R. Okay. Similar for KATL.
Yeah. So lastly, I want to say our work can augment the existing airport surface surveillance capability by providing this additional risk and conformance monitoring capability, because currently it's only taking the radar signals from different bands, but they are not taking the communication signals in ASSC. So that's our selling point. Thanks.
Any questions from our steering committee members?
I'll ask one. These kinds of, I mean, this is really fantastic work and integrate the comms with the surveillance. The barrier in the past has often been that the error rates are too high, right? And so you generate a lot of false alarms. Do you think that we're past that now? That the whisper models with the training are good enough that it would be? I mean, I don't know what good enough is, but I mean, is it significantly better than previous generations?
Yeah, the false alarms definitely is an issue for any kind of safety warning system for civil aviation. For this work, frankly speaking, we didn't pay too much attention about false alarms, but I think it's reducible by sensitivity or by parameters tuning of the model. Basically, I think we should include the false alarm reduction technique in the risk formulation.
When they first did it, they didn't have the 711065 in there, and there was a lot of errors in the transcription. But because there's so much structure in the way we communicate, that helped to reduce the errors a lot. So I think the false alarms are manageable.
So kind of building on that, it's John Marimo. Similar question, maybe the same question. It's, when you're talking about the ASR, the whisper, and its effectiveness and the work that's out in the world today concerning that model, and when you try to add the .65 to it with real world communications, which has a lot of variability. So although I heard the gentleman mention the structure, there's certainly structure, but as I'm sure you've encountered, the more natural controller pilot communication is wildly variable. So I'm curious as to what that kind of effect had on your NLP side of the equation, and where you saw success or failure.
Yeah, thanks for the question. So I think first of all, for all those OCR or speech-to-text engines, they are still rapidly developing. So we are still expecting some better solutions or better state of the art year by year. And of course, we use the rules to augment or enhance or override the existing tools because we want to adapt to the domain, which is air traffic control. And I think that's basically something we are specifically interested in. But of course, this proposed thing is only intended for nominal conditions. So if there's any off-nominal conditions, which the communication just don't really follow the standard rules. And I'm thinking maybe some other formulations, such as, because the current formulation is basically NER, which is basically named entity recognition, which can only recognize the predefined entities, which is flight cosines intents. But if there's an off-nominal condition, we can use some large language model or language understanding or contextual understanding technique to contextually understanding what's happening between the pilot and the ATC. And that's, of course, that's some second assurance or additional functionality or additional module for this.
Yeah, that makes sense. Before I let my friend Steve jump in with a question, my follow-up is going to be, taking a step back in the big picture, what's your thought? What do I do with all of this? Is this a tool sitting next to a controller that somehow alerts of a potential problem? Is this a post-analytical exercise? What is your thought?
So the initial idea of this work is we want to propose an additional functionality for the airport surface surveillance capability, because currently ASSC can do like conflict detection, conformance monitoring on the ground level, situation awareness. But we look at the data source ASSC is taking, it's only taking several surveillance data, radar data, ground movement data, of course, different band, X band, crew band, whatever band, but it's not taking the communication transcripts, which is important to understand. Like intuitively, if we understand the intent of what are the pilot and ATC communication trying to say, that's important. So that's why we are trying to say, we propose this thing to augment ASSC, which is some system which is an upgrade of ASSC, I would say. That's our initial big picture idea. Yes. Thanks.
Thank you very much. Tackling a really interesting problem. Thank you.
So I can be really quick because John basically took my question, but I can have a different flavor of it. So I was also wondering, so first of all, I appreciate the rigor of this analysis from like a retrospective perspective, but in the real-time application of it, do you think that this model with current technology could produce outputs quick enough to be used in a real-time environment?
Yeah, we believe this technique is capable to perform this work in real time in the real world scenario. So we conduct the complexity and we conduct the time and space complexity study for different machine learning models used for the NER. So if you so NER is a technique to fine tuning based on some foundations, and the foundations can be any like local contextual, global contextual, or even generative AI based, or even distilled models just for smaller size and even multilingual models. But it's up to which embedding or token level embedding models you choose. So you can have a balance between space-time complexity. And based on, so we put the figure of this study into the original report, but unfortunately we didn't put it here. But we can achieve really quick or really fast NER scanning by using some local contextual model, which is a token to vector embedding model. So we believe this work is realistic for real world usage. And the second part of the work is basically risk calculation. So it's basically some simple like double float mathematical calculation. So it's really fast for computers. Yeah.
I'll just add that, especially on the second part, because we have an analytical solution for the risk, it can be done in real time. So everything is doable in real time.
Yes, we are not using Monte Carlo simulation, but we use some assumptions to approximate the risk. So we get an analytical solution. Yeah.
Thank you guys. Excellent. Next up is University of North Dakota, sentiment and pattern evaluation of ATC keywords. All right. Well, first we want to give some thanks. So thank you to the FAA for putting on this challenge. I also want to thank HeroX for facilitating this challenge. Also MITRE for hosting us. And I want to get started by putting you guys in a scenario. I want you all to imagine that you're air traffic controller for the day. And let's use New York, really busy airspace. And it sounds something like this today.
090, just want to maintain 3,000. 090, just maintain 3,000, 4129. Number 4518, speed 210, then maintain 4,000. 210, then down to 4,000, number 4518.
Now, I understand that we're not actually air traffic controllers, but you can see that it's pretty busy. And what's interesting is this is normal operations for New York airspace. And now say you have a frustrated pilot on the radio saying stuff like, "Don't tell me what to do." Moments later, they almost cause a near miss because they didn't follow your instructions. This is an example of anti-authority, and it poses a significant risk in the national airspace system. Now the question becomes, what if AI can detect this in real time? My name is Zach Hoff. I'm a double major in commercial aviation and aviation safety. I'm also a flight instructor at the University of North Dakota.
My name is Caroline Kelly. I am also a major in commercial aviation and aviation safety, and I am also a flight instructor at UND.
My name is Andy Aikenson. I am pursuing a master's in science in aviation safety, and I'm a commercial pilot.
And our research focuses on AI and machine learning to analyze ATC communications, detect hazardous attitudes, and improve safety in the national airspace system. Now, to do this, I want to go over a roadmap of what we're going to be talking about today. So first, we're going to establish the background. So we're going to explain what are hazardous attitudes and why do they matter. Then we're going to explain the problem, talking about different human factors in the aviation industry. Third, we're going to go over our solution. So how are we going to use AI and machine learning to analyze air traffic control data? Then we're going to talk about our methodology, so the details on exactly how we use it. Then we're also going to use testing and evaluation to explain our accuracy, some of the challenges that we faced, and then talk about the application of our project. And then finally, we're going to conclude with a brief summary and talk about the future potential of our project. So what are hazardous attitudes? Essentially, they're patterns of thinking that can negatively impact decision-making in aviation. And the FAA has identified 5 different attitudes. First, we have anti-authority, which we just talked about. This could be an example of ignoring instructions and doing whatever you want to do. We also have impulsivity, which could be rushing a clearance. So say you get a takeoff clearance and you don't double check something and you just decide to go quickly. We also have invulnerability. So this is where you're, for example, flying into bad weather, even though other pilots aren't, ATC is telling you not to, and you decide to do it anyways, saying it's not going to happen to me. We also have macho, which could be doing dangerous maneuvers to impress others. I like to think of Top Gun for this one, some of these kinds of maneuvers. We also have resignation, which can look like giving up problem solving and thinking that you have no other options. Okay, now that we've defined what hazardous attitudes are, why do they matter? Well, first, and essentially, hazardous attitudes equal a major risk in aviation. Hazardous attitudes contribute to 86% of all fatal general aviation accidents. But it's not just a general aviation issue. We also see it in airlines. For example, Pinnacle Airlines Flight 3701. In this situation, we had 2 pilots that decided to climb up to flight level 410. Now, this is well within the capabilities of the CRJ-200. However, they had a dual engine failure at this altitude. They were not able to restart their engine, and they ended up crashing, killing the 2 pilots on board. In addition, 77% of ATC facilities are short-staffed. So this has become an increasing problem in our airspace. This increases stress, fatigue, and workload, which could all increase the chance of miscommunication between pilots and air traffic control. So with hazardous attitudes contributing to most of the fatal accidents, in ATC under pressure, AI and machine learning can alleviate stress and mitigate the risks that we see.
Our solution to this problem is SPEAK, which stands for Sentiment, Pattern, and Evaluation of ATC Keywords. Our methodology for creating SPEAK can be outlined in 4 major steps, which are data collection and pre-processing, followed by our speech-to-text transcription, followed by sentiment capture, and lastly, our analysis and interpretation. I'll cover these more on the following slides. First up, we have our data collection and pre-processing. For this step, we utilized a variety of sources. First, we have the NTSB accident database. For this source, we searched keywords using their search feature, and we used hazardous attitudes. From there, we grabbed any transcriptions that were attached to the accident reports that identified these hazardous attitudes as factors for these accidents. We also utilized recordings from liveatc.net, as well as YouTube videos that showcased interactions of interest between pilots and ATC where hazardous attitudes were present. To wrap up this step, we trimmed any longer interactions to only include the relevant context and the hazardous attitude itself, as well as converted the YouTube videos from MP4 format to MP3 format. Following this step was our speech-to-text transcription. After our research, we settled on using OpenAI's Whisper or Whisper AI. We decided to use this platform because of its capability to transcribe technical jargon, accents, and language, which are all common in aviation dialogue. Here's an example of the success that we had with Whisper AI. You can see outlined in this, we have lots of the phonetic alphabet, which is commonly used in aviation, as well as headings that are given to the pilots, and it was able to transcribe these very well. Our next step was the post-transcription processing. First, we standardized the text and removed any extraneous data. We did this using code, and we followed a standard format of all lowercase text, removed any punctuation, and any extra white space that was left. From here, we labeled the data set with hazardous attitudes, and this was a manual process for our team. With our experience as pilots, we looked at the transcriptions and decided which hazardous attitude applied best.
Following our data collection and pre-processing steps, we assigned polarity and subjectivity scores to each of the dialogue excerpts. So what this looked like is our polarity score is from a range of -1 to +1, where -1 represents a negative sentiment, 0 represents a neutral sentiment, and +1 represents a positive sentiment. One thing of note is that though hazardous attitudes naturally have a negative impact on the airspace, some of the dialogue verbiage that is used in those excerpts can in themselves be positive. In addition to this, we looked at the subjectivity of the statements where 0 represents a fact and 1 represents an opinion. Once our methodology was determined, we implemented this code, which used the text blob functionality in Python in order to assign scores to the different pieces of dialogue. So in this example here, we have the definitions of each of the hazardous attitudes to give an example of what that looks like. And here are the scores associated with them. You can see that there's some variation, but we'll look a little bit deeper into that in the next slide. And here we can see a heat map of the scores of, this is polarity scores specifically, where the red and orange colors represent lower polarity and the green and yellow represents higher polarity. So even with this small data set, we have 11 examples of each hazardous attitude. You can see trends start to emerge where with resignation, for example, we can see that there's a low level of polarity. So typically when that hazardous attitude is shown by a pilot, they tend to have a negative tone with that, versus maybe invulnerability, for example, where there's more of a positive sentiment behind the statement that they're making. Similarly, this is a heat map of the subjectivity scores. Same kind of process of interpretation here, just applying that subjectivity instead, where in this case, resignation has a higher score, so it's more of an opinion-based statement, versus impulsivity, for example, which is more of a fact-based statement. The ultimate goal of this is to use these scores to create a tool for ATC that can be viewed as a trend graph that'll depict how a hazardous attitude develops over time. Here's an example graph which represents the polarity and subjectivity scores of multiple consecutive statements from a singular pilot who's exhibiting the resignation hazardous attitude. To supplement our sentiment analysis, we use the AI BERT model, which is a pre-trained model that leverages AI and machine learning, as well as natural language processing, or NLP, for hazardous attitude identification. So here's an example of some of our code, which was used to load our data into the code, as well as any applicable libraries, as well as normalize the data group, as Andy mentioned, with making sure that all of our data set is uniform. From there, we tokenize the code, which breaks the dialogue down into meaningful units of text in either words or subwords, and then created tensors, which convert the words to numerical values in an almost matrix format, as you can see here. And then we created our custom data set within the code. And then we split that custom data set into 2 groups, one for training and one for validation. So the training set will train the model, and then the validation set is used to test the efficacy of the model. Here we created metrics that would evaluate our model, including evaluation loss, accuracy, precision, recall, and F1 scores. And then from there, we were able to create, train, and evaluate our model, as well as load it. And then this code shows an example of how we created a prediction formula, which allows the model to predict what hazardous attitude is being demonstrated by a pilot. And then we created a chat bot as well, so you can input the text, and then it will return what hazardous attitude is being displayed. So here's an example of that, where we input the definition of impulsivity, which is do it quickly, and the model correctly identified that hazardous attitude.
Following this was our testing and evaluation process. As Caroline mentioned, we completed a comprehensive testing process using our BERT model. From this, we were able to observe positive performance insights, which also helped us identify future improvements that need to be made. So here is an example of our BERT performance metrics. We have our evaluation loss on the left. With this, we want to see the value going down, which we did. And all of our other metrics, we see the values increasing, which is another sign of our BERT model observing the model being trained to better predict the hazardous attitudes. Overall, we do have some improvements that need to be made. Our model's not perfect, but all of our metrics are trending in a positive direction.
And with all these metrics trending in a positive direction, we can confidently say that we've demonstrated that AI and machine learning can detect hazardous attitudes in ATC communications. Speak shows promise for real-world application in air traffic control training, safety monitoring, and also hazard prevention. Over the challenge, our team learned a great deal and a deeper understanding of AI, machine learning, NLP, and aviation human factors as well. Like Andy mentioned, there's some work to be done, and some future improvements that we would like to make is to develop the AI model to be more real-time and not just post-flight, so then we can get immediate identification of hazardous attitudes in real time. We also want to expand our data set with more transcripts and more diverse scenarios, and overall get more ATC and pilot interactions. We'd also want a cloud-based system for better scalability and accessibility. And finally, we'd also want to validate AI performance in real ATC simulators and real scenarios as well to test the real-world effectiveness that we aim for. By enhancing real-time analysis, expanding our data sets, and integrating Speak into training environments, we move closer to making AI an even more valuable tool to improve aviation safety in the national airspace system. Thank you.
Hi, it's John Berdimo again. Outstanding work. I had made notes on this before, obviously, because we're all judging, and your presentation has backed up some of my notes in that it's very interesting outside of the box thinking, and having spent some time with our human performance, human factors teams and in the ATO safety environment, it's very interesting to try to quantify something quantitatively that is so subjective. And it's really intriguing to try to reduce that risk. And it's an area that the FAA is actively trying to work on. And I think you've hit on something very interesting here. From a question perspective, the conversation, it appeared to me when reading the paper that you would have the controllers kind of review or otherwise determine how the information is coming across. It kind of gets to the question of how you would do like development assurance in general and what those assurance objectives might be. So I'm wondering if there's a connection between the use of the controllers as a shortcut or a more inexpensive way to get that done versus some more expensive in resource and time version of assurance.
I think our perspective on that was we really wanted to ensure that controllers are part of that conversation and they're at the table because it's a tool for them to use. So we want to ensure that they actually feel that it's alleviating the pressure that they're facing in their work.
And to add on to that, yeah, like you don't want to increase their workload any more than it is with a tool that's not even going to help them. So this whole goal is to help them. And also we'd want to include them in the conversation with training so that they know how to use it and that they can also like put input in what they actually are looking for.
So
yeah,
to follow up on, oh, sorry, go ahead, John.
Just thanking.
Okay. Just to follow up on that a little bit. I mean, jumping directly to real time sounds challenging in the sense of, how would we present the information, so on and so forth. Maybe there's a intermediate step of interest, which is for pilots to use this kind of tool in their own, to analyze their own behavior in a sense, and have it feed back to them, even later, analyze, what you did today and say, hey, seemed like you were a little impulsive, maybe.
Yeah.
Or something like that. And that would be a non-safety critical way to essentially, validate that you're getting useful results or something.
Yeah, thanks for the input. Like as a pilot myself, like I know like which one I would probably lean towards, and with my students, I can see different hazardous attitudes. So yeah, like a post-flight analysis on pilot behavior is definitely good. Yeah, thank you.
I agree. I appreciate that feedback. I also think it'd be very valuable in the training environment specifically, which we're deeply involved in, and be able to show students, hey, this is kind of what happened during our flight today.
Jason, I don't know if you were ahead of me. I saw you had your hand up.
Yeah, I
Go
did.
ahead,
I'm
Caroline.
sorry. Go ahead. Yeah, sorry about that.
Okay, no worries. I'm a little interested to hear more about how you went about manually labeling the hazardous attitudes within your data. I know in the presentation you kind of had like one phrase for each hazardous attitude. Obviously, it's going to be a lot more complex than that and maybe not as direct. So if you could talk a little bit more, please.
All right, so absolutely. So what we did is, like Andy mentioned, we looked at different sources of transcriptions, whether it's liveatc.net or the NTSB or YouTube. Particularly YouTube was very beneficial for us because we were able to, they had already curated specific events of interest where we could find hazard attitudes a little bit more readily. And what we would do is we would just take pieces of dialogue and then we would assign the hazard attitude that we felt best fit that piece of dialogue. And there is going to be some subjectivity associated with that because it is a little bit of an opinion-based assessment. But we kind of all took a different perspective towards that and corroborated with our separate opinions to come up with the best representation of what hazard attitude is being demonstrated.
Awesome, thank you.
Yeah, great job. I think from a training perspective, this solution makes a lot of sense. Air traffic controllers audit their own transmissions from a management perspective. I was interested from a real-time solution. If you were able to integrate that into ATC operations, how would you anticipate a manager getting an alert that there was some sort of hazardous attitude going on, and then how to respond to that?
Yeah, I picture like they're in the cab and then they get that alert and then they refer to their training and there's like mitigation steps for each of the hazard attitudes. You have the mindset, which we had on the slides, but then you have the fix, if you will. So I see them using that fix to help either calm down the pilot or reassure the pilot. I know there's been many times when I've been on the radios and I hear someone getting a little agitated or they're nervous. And I like to see air traffic control's like response to that. So I think with the increased training and seeing that it's happening, especially when it gets busy, they maybe can't listen as deeply into like the tones and stuff going on. So I think once they get that alert, they can go back to their training and try to think of the fix and help bring that pilot back to like a certain baseline.
Great, thank you.
Other questions? We have just under 2 minutes.
I have one. I have a quick question for you guys. First of all, amazing job on this. Have you thought about crowd training models and picking up on keywords? Because there's some really insignificantly small models out there where you can have a keyword that you're looking for, like no, and then you could count how many times somebody says no in a huge crowd. But then putting that into a model and then training on that model over and over and over again, thus streamlining your original model. Have you thought about any of that, like taking it out of the context of, say, air traffic controlling, but using it in a crowd scenario to train your model with?
We haven't specifically considered that aspect of it. We did consider generating sample data as, we can kind of come up with our own statements that would represent those hazard attitudes, but I definitely think that that would be a great direction to take this project.
And kind of go with that too, like certain words like unable would be a good one. Mm-hmm. So pilots will say unable if they can't do an air traffic control directive. So kind of digging in to find those moments when they say that, what's leading up to it and what's happening after that would be definitely beneficial, like you said.
Yeah, or if people are just yelling in general, you can like kind of catalog that as something different. But yeah, good job, guys. This is very enlightening.
Appreciate it.
Thank you.
Started. We're going to resume for the afternoon. We have 2 more presentations. So the way the afternoon is going to go, we have 2 more presentations. Then we'll have an afternoon break. That'll be a longer break because the steering committee will have their deliberations to pick the winners. And then we'll come back for the award presentation. Now, we have 75 minutes allotted for the deliberations, but we anticipate we will be done sooner. So don't go too far. And then we'll try to gather everybody back, make sure that we have everybody before we start the award presentations. So we're going to start now with University of North Texas, Weathering the Sky, GNNs for UAV micro forecasts. Second.
Good afternoon. We are with the Department of Electrical Engineering, University of North Texas, and this is Weathering the Sky, GNNs for UAV micro forecasts. First, I'd like to introduce the team. Our faculty advisors are Dr. Kamesh Namaduri and Dr. Colleen Bailey over there in the back. My colleague, Ben Hand, and I'm Gavin Halford.
So, that was louder. Unmanned aerial vehicles are going to be a part of our future. They're going to help revolutionize transportation, delivery, emergency response, and countless other applications. But before they're a part of our daily lives, there are lots of safety concerns that we need to take care of so that way no one gets hurt and nothing gets damaged. One of the biggest safety concerns is weather and how a small change in the weather can drastically impact UAVs of all different sizes. Currently, there are no weather forecasting methods that have enough granularity to properly assist UAVs in their operations. Because of how small of a weather change can affect UAVs, there's just no system that has what we need. So we need to have an accurate micro weather forecasting system. So this looks like having weather sensors put onto UAVs in order to help kind of build a better weather picture of what's going on. So once we have that better weather picture, we have to have some kind of way of analyzing it efficiently and making the data useful.
Like Ben said, one of the ways to add resolution to the air corridor is by real-time weather data within that corridor coming from drones that are operating. The goal of this project right here. The goal of this project right here is to kind of create this infrastructure that can take that data and interpolate it throughout the rest of the air corridor. And for that, we have chosen to use graphical neural networks because they handle spatial data better than more traditional models. And the reason that they do is because we can establish nodes within the graph. And in those nodes, we can put features. And the features are your sensor data. It's whatever you want it to be. And then we can make connections between those nodes based on edges and edge weights. And for that reason, GNNs are just a little bit better at handling dynamic spatial dependencies. So this is how we picture the air corridor. We fill it with a collection of equidistant nodes with 0 features. As the drone flies throughout the corridor, collects that data, specifically we're focusing on wind vectors. We map that wind vector to the closest node. And then we use the GNN to interpolate that data throughout the adjacent nodes based on the edge weights that we've already established. The more drones we have in the air corridor, the more complete of a weather picture we can establish.
So unfortunately, there are no publicly available data sets that are representative of weather within an air corridor. So we had to go elsewhere to find data to kind of use in order to prove our idea. We were able to find a NOAA data set for buoys within the Chesapeake Bay. That doesn't necessarily seem like buoys in the water are representative of drones in the sky, but there are a couple of reasons why it's exactly what we were looking for. The first thing is it's real weather data. So it's everyday weather sensors that are on each of these buoys giving us wind speed, direction, temperature, different things like that. And then they're also spatially and temporally consistent, meaning that temporally, they are taking a lot of data at very consistent time intervals, and then spatially, the data is not moving, or the buoys are not moving that much. Specifically for our project, we took 3 years worth of data from 5 different buoys. These buoys range from about 30 to 120 kilometers in range from one another. Because of this distance, we set a threshold of 75 kilometers to determine which buoys will actually impact one another. You can see that here based upon the red lines. So for example, the Potomac buoy only has one other buoy within the threshold, Stingray Point. And so the only buoy that Potomac will interact with and will be affected by is Stingray Point, whereas Stingray Point is within the threshold of all the other buoys. So they will all impact Stingray Point and it will impact them.
Whenever working with raw sensor data, you got to do a lot of pre-processing on it to actually make it usable before you feed it into the model. One of the things we wanted to figure out is temporally, how much the features change over time and what is the cycle for those feature changes. We're dealing with weather data, so it makes sense that the weather is going to be consistent and it's going to change over a daily cycle, a yearly cycle, or seasonally cycle. We drew this out using a Fourier transform, and we decided to focus on the daily and yearly cycles. We took the timestamps of this data, we sine, cosine, and coded it so the model can better understand those variations as it flows. And with that, then we kind of aligned all the rest of the data to follow that sine, cosine, and coding to help the model predict that way. So everything was, the wind angles were sine, cosine, and coded, and all the rest of the feature data was mapped to that -1 to 1 range. Additionally, we took the training data set and essentially it's 3 years worth of data collected every 6 minutes. And we wanted to save that temporal aspect, but we also wanted to add some randomization to the training data set as well. So what we decided to do was to group them in months and then shuffle the months, right? And with that, we wanted to make the system a little bit more dynamic. So instead of just predicting one buoy all the time, we started cycling which buoy we were going to predict to more closely mirror the end state, which would be a changing node, which is what we would be predicting. So the ground truth buoy shifted every month. And then we also masked all the rest of the weather features to make sure that we weren't leaking data into the prediction aspect of the model.
After all of the data pre-processing, we finally get to the machine learning model. It starts off with the GNN layer, which handles the spatial data and understanding those spatial relationships. After that, it goes into the GRU layer that looks at the temporal and time-based relationships. And then it ends with a dense layer making the final decision of the model. A couple things that we had to do in order to improve the model accuracy. We're adding a hybrid loss function that we had to come up with, combining cosine similarity and the mean squared error. This was used to specifically improve the wind direction accuracy. We also had to do a lot of normalization and using leaky ReLU to prevent the vanishing gates problems that we were having. This is because we had a lot of negative data, so we had to use something in order to interact with that data instead of completely ignoring it. Looking specifically at the spatial part of the model, so we defined the edge weights between the buoys based upon their angular relationships with one another. So for instance, we look at the wind vector 1, it has a pretty low cosine similarity in comparison to wind vector number 2, meaning that we're going to assign more weight to wind vector 2 as it relates to buoy number 2. So that way, whenever buoy 2 is making its predictions, it's going to be a little bit more influenced by the wind vector 2.
Excuse me. So initial model design, we had a couple different variations for GNNs that we were looking at, and we decided to test 3 variations. One was the attention, the graphical attention network. The other was the edge conditioned convolutional network. And then the final one was a hybrid between multi-head attention and graphical attention. The way we determined the best performance was over groups of epochs, 10, 20, 30, and we would monitor loss, MAE, and how gradients flowed throughout the layers within the model. Gradient stability was very important because if your gradients got too high, the model would get unstable. And if they were too low for certain layers, then you were just wasting time because that layer wasn't actually contributing to your model learning efficiently. At the end of the day, we found that the edge condition convolutional model performed the best. And this actually worked out really well because this gave us more ability to determine what those edge weights were. So how to do? For wind speed, we were highly accurate. We were at about 0.06 meters per second MAE. Angles was not quite as good. We were about 49 degrees average error for the whole test set. So there were groupings where we got real good, but for the whole test set, we kind of started skewing outward. And part of the reason is, the circular nature of angles in relationship to a buoy is kind of hard for the model to differentiate. We improved this through the custom loss function we designed using cosine similarity, but there is still some more work to do. Finally, we need to compare the results of our model to something else, but there wasn't a lot of options out there on a data set like this. So what we decided to do is go with a couple more traditional heuristic methods for wind vector analysis, one being the persistent model with an amount of decay, as well as the nearest neighbors model, which uses kind of the closest buoys and a set level of decay to interpolate what the ground truth buoy data is. As you can see, our model did perform way better than both of those models.
Throughout the process, we did run into several challenges. First being the data sparsity. So the distance between the buoys was far more than we would have liked them to be, causing a lot of error that we had to correct for. On top of that error, there was also sensor error. The sensors on the buoys were quite old. The data has been collected for a really long time, so there's just naturally error that had occurred within them. And then also the normalization issues we had talked about previously. There's lots of future work that we see for this project. The biggest thing is getting a newer data set that is more three-dimensional compared to the two-dimensional data we've been using for this project. Also looking at other applications for this model. It's a super diverse model, so just being able to use it for different things. One idea that we've been exploring is using it to determine what sensors might be having some faults in them, trying to figure out where those are and how consistent it's happening. So overall, we were pretty successful in the project. We were able to determine that GNNs are a very effective method for micro weather forecasting. And out of all the models that we tested, the ECC-Conv performed the best compared to our other models and the comparison models that we were using. We definitely proved the viability of this project and justifying further work in the future. So thank you all for your time, and we're open to any questions.
So when you put the picture there has all these buildings around it. The ones that you had, were they close to buildings? Because you have the wind tunnel effect around buildings. And it would be really cool if you could actually predict around corners.
So there is some future work established with that. If you look at where our buoys were situated, some of them were more inland from the Chesapeake Bay. So you did have like a wind corridor this way, and then you had offshoots going into more inland areas. So there was, even though there was a connection there was some level of topography that was kind of impeding that. With the edge weight connections that we can establish, we can get as complicated as we want with those, right?
Because the image there is, that's one of the issues that a lot of people with the package delivery don't understand, that buildings are going to be an incredible creation of gusts and stuff like that. And so being able to predict around corners with a sparse, like a problem of trying to find a minimum number of drones required in situ.
That's exactly right. So what is that number of drones for that size airspace to give us the best picture of what is happening in there? Right now, what's happening is, we get altitude data once or twice a day. And then as we get the weather picture come in, the whole swath of the air corridor gets shut down because, we just don't have great enough visibility. And we're hoping with something similar to this, along with the on-drone sensors, that we can provide a better picture of what's happening out there.
Okay, thanks.
So I think building off of his comments, I think a challenge is putting those sensors on drones, right?
Yes.
Because for every ounce at this point, you're adding, that's dollars a shipper can't. So have you considered in that scenario, putting these sensors on buildings
at least for those metroplexes where that's more of a problem as opposed to, say, a rural area?
So that's a great comment. Our current air corridor is outside of, it's not this, right? Right. So like this is kind of what we're working with. To your point about the dollars as far as the sensors go on the drones, one of the reasons we chose the buoy data was because it is as basic as you come. Like the sensor data is just, here's your wind speed, here's your direction, right? So like these drones on the sensors are going to be, we want them to be simple, right? Simple but consistent. And I think with enough of those, right, we can create a better weather picture within that air corridor.
And to also build off of that, I think taking in, so long as it's the same information, as much information as we can get is going to improve accuracy and make the model more robust.
Yep.
So adding those, whether it's buildings or something else, it'll still be valuable information.
Any questions online from our steering committee members?
I was just curious, could you have the entire network on fixed locations, buildings, and does it have to be on drones? Is the reason that you put it on drones that they would cover like a larger geographic area?
So the reason that we're putting them on drones is because we don't actually have in our current air corridor structures within that air corridor. So if I have this wide open expanse, the only place I can actually take sensor readings within that air corridor is on the drone itself. Now you're absolutely right. If that air corridor gets moved towards city centers or stuff, we can start collecting data on fixed surfaces. But right now, all of the data collection is happening outside the air corridor, and we're making big approximations for where that weather is impacting the corridor itself. So essentially the whole corridor gets shut down based on some of the weather models we're getting, and we'd like to have that more granular based on what's actually happening within that air corridor.
Yeah. Yeah, because I know you can talk to weather folks, experts in weather. They use all types of sensors, balloons, all different types of vehicles, right? So that's something to maybe investigate.
Yeah, and I think that would be a future state where we could use the weather sensor within the air corridor and kind of put it with the radar data to get an even better picture. We were kind of looking for some kind of infrastructure to take that really basic data and try to interpolate it as best we could to create a better picture to kind of disperse out to those other simulation models.
Question, have you, so I mean, we've been sort of focusing on what feels like the drone package delivery concept. Have you looked at applying this to other types of operations like AAM, air taxis, where maybe the size of the vehicle is a little bigger? And so using that kind of aircraft as an in situ weather sensor would be maybe more feasible.
Yeah, absolutely. It just for where we are in Dallas, our air corridors are in the very early stages, and AAM is definitely a big thing that's going to be happening out there. We kind of built this to the smallest denominator, right? So we kind of wanted to say, okay, with the smaller drones that are going to be most affected by this, how do we get that sensor data, and then how do we promulgate it through the rest of the system? But you're absolutely right. The bigger air taxis are going to have a higher capability for collecting better data throughout that air corridor.
Thank you.
Thank you.
Okay, if there are no other questions. Thank you.
Oh, yeah.
Thanks a lot.
Yeah.
All right, next up, our final presentation will be from Oregon State University and Drexel University. So probabilistic risk assessment using REACH.
Hello. All right. Last presentation. Let's do this. Hi, everyone. I'm Nicole. I'm from Oregon State University. I'm joined by my colleague Hari from Drexel University. And today we'll be telling you about PREACH, which stands for Probabilistic Risk Assessment using Reachability for UAV Control. Hari mostly focused on the risk assessment piece. I focused on the UAV control piece, and together, or our pieces came together through this thing called Reachability, which we'll tell you all about soon. But first, a note on what the current state of the UAVs are in the NAS. If you wanted to fly a small UAV, right now you'd have to file what's called a Part 107 waiver with the FAA to get approved for operations over highly populated areas like dense cities, or if you want to fly at night, or if you're flying over a far enough distance that you'll eventually lose sight of your drone. Or any number of operations that are listed on the FAA drone zone site, you'll need to file this waiver. And this waiver requires you to list all possible risks you might face operating your UAV and how you might mitigate those risks as an operator. So, for example, if your operation is to use a UAV to deliver medicine over a group of city blocks, say in Philadelphia, where this population density map comes from. So the bright yellow and light green areas indicate areas where there's high population density, and the dark blue and purple areas indicate areas of low population density. So a nominal UAV trajectory would be, for example, this dark blue line, but say some sensor error occurs that causes the drone to take on this red dashed line trajectory that brings it closer to this highly populated area, increasing the risk that if the drone were to lose control and fall out of the air, it would hit a person on the ground. So one of the key questions we want answered as part of those Part 107 waivers would be, what is actually quantitatively that risk of a UAV colliding with someone? And how can we control the UAV to then bound that risk below some acceptable threshold? Before we get into how we can answer those questions currently, a brief clarification on what we mean by risk. So risk is the probability of some event occurring times the severity of that event occurring. So an event can be, like in the previous example, a drone hitting a person. And so high risk events can be those that don't happen very often, but are have high severity, or they can be events that happen a lot but have low severity. In our work, we treat all events, or we're considering all events to have equal severity, but it can be generalized to other models of severity.
Thanks, Nicole. At this point, I'd like to mention or bring up 3 documents. The first is a report commissioned by the FAA with the National Academy of Sciences, Engineering, and Medicine in 2018. It was titled Assessing the Risks of Integrating UAVs in the NAS. So this document formed like a philosophical guide for our work, and we based at every decision point, we based our the outcome was decided fitting with the philosophy that has been recommended in that document. The second document is the 8040C.4C, which is an FAA order, which is the Safety Risk Management Policy, the SRMP. And the third is the Safety Management System framework, again prescribed by the FAA. The reason I bring these 3 documents are that we have tailored the work based upon the guidelines that have been prescribed there and the requirements and needs that have been identified there. So one of the recommendations of the SRMP is to have a quantitative measure of risk, and it prescribes a 5-step process, which starts with system analysis, then hazard identification, then risk assessment, risk control, risk mitigation. Risk quantification, assessment, and mitigation, right? So the probabilistic risk analysis has been present way before UAVs existed. It's a well-studied method that works well for processes that have been, which have existed for some time, with a good amount of data to work with, right? And that is, so what we have done here is fit the blocks of components that go into a probabilistic risk assessment within the silos of what I imagine would be close to the FAA's definition of a ConOps operation, from ConOps definition to risk assessment to finally making the operational decisions, right? So this is how classical PRA works. Yeah, but there are some shortcomings with it. The analytical formulation that underlies PRA is very strong, right? But there are some shortcomings with it. The first thing is, I think this a common thread in most of the projects that we have seen today is the limited historical UAV data. So the equations on the right, that they are basically the engine that drives probabilistic risk and classical PRA. It's simply a Bayes theorem and a total probability theorem. So you identify a list of hazard causes that might lead to hazard outcomes. We are interested in the probability of a hazard outcome occurring given a particular hazard cause, right? The issue is that we do not have good structured data that we can feed into the equation to find the actual risk of a hazard outcome occurring given a hazard cause, right? So that's the first major stumbling block to applying classical PRA. The second is that when you have less data, we have to naturally make more assumptions, right? So because there is a problem of balancing data fidelity and model fidelity along with analytical tractability, right? So if you have less data, we have to make more assumptions. And one such assumption is, for example, classical PRA restricts itself to binary categories of hazards. That is to say, whether a wind exists or a wind does not exist. It can, but it does not handle this notion of what is the risk if over a particular range of wind speeds, right? So it doesn't answer those questions really well. The third shortcoming of PRA, classical PRA. Now, even if you had data, assume you had data, one of the things that distinguishes UAV flights or UAV operations from general aviation flights is the sensitivity between the risk and the ConOps specificity, right? So, for example, if we have, UAV incidents and collision data, and you have all data relating to hazard causes and hazard outcomes, say over a semi-metropolitan area, right? Assume you have to start from the center, and then you have to deliver drone packages. Now, we have identified some hazards there. Clearly, if your drone is flying over, say, a Taylor Swift concert, the chances of it colliding on somebody is very high. If it's flying over a rural farm, the chances of collision with a person are low. If you have an airport in the way, then you run the risk of flying into a no-go zone, right? So these are all different types of hazard outcomes that have been laid out. The issue is if you have the data for the entire region, you basically are averaging the risk over the entire region. But because our UAVs are so ConOps specific, what we'll end up doing is underestimating the risk in some cases and overestimating the risk in the other cases, right? So we want a method that is a little more trajectory aware when it performs its risk analysis.
Yeah. So this is where our method, PREACH, comes in. PREACH is a model-based risk assessment framework, and I say it's model-based because it relies on the dynamics models of the UAVs. So unlike classical PRA, which is basing its risk assessment on this limited historical UAV data, PREACH doesn't need to use that data. Rather, it can rely on publicly available, readily accessible open source data, such as data from Google Maps or OpenStreetMaps or population data from the government that, for example, we use to create that population density map we saw earlier. The other shortcomings we address are that where classical PRA is only applicable to categorical hazard causes, PREACH can handle continuous hazard causes. So we can incorporate and model wind speed, for example, in our risk assessment. Where classical PRA averages risk over all possible areas that a UAV can go, PREACH computes its risk assessment based on where the the UAV can actually go informed by the actual dynamics of the UAV. And where classical PRA focuses on, or is all done basically pre-flight and makes its decisions before anything takes off, Preach is actually able to make in-the-moment decisions, make risk assessments based on data collected online or up-to-date information about where the UAV actually is. For example, it can compute controllers that are risk-aware in a way that is not actually like even considered under classical PRA approaches. So here's an example in simulation of what Preach can do. So in both graphs, we see that population density map we saw earlier. The dark blue lines are the nominal trajectory, and the orange lines in both graphs represent two different trajectories under two different types of controllers in the event of some hazard cause causing the UAVs to drift. So on the left here, or my right, but your left, we see that this orange trajectory is going over this highly populated area, and it's actually just taking a riskier trajectory. Whereas on the right, where we are using Preach, the trajectory avoids that highly populated area and overall produces a less risky trajectory. And the key to Preach being able to do this are these blue rectangles here, which are called reach sets. So reach sets encompass all possible or feasible trajectories that a UAV can take based on its dynamics, and that's what we use to evaluate risk over. So with this risk evaluation, we can then minimally change the UAV controller to maintain bounded risk below some acceptable threshold. So as I said, reach sets are the core to how Preach works, and reach sets are computed using reachability analysis. So this is a process in which all possible states a dynamical system can take are computed given an initial state or an initial set of where it could start. So say the UAV starts in this initial gray set, which is over approximated with this gray polygon. We can use the dynamics of the drone to then project a future set, and then the next set and the next, up until some established time horizon, where in this example, we can see that this final reach set intersects with the unsafe region. So we use this notion of reach sets in the rest of our components of Preach.
So once we have identified the reach sets, this slide talks about how we actually do the risk assessment, right? A classical PRA basically uses a frequentist approach or a Bayesian approach, depending on what sort of data are available, or what sort of assumptions you make on the priors, which makes them trajectory agnostic, so to say. Because of the fact that we use the system dynamics to inform the reachable states of the UAV, we decided to try a stochastic approach and model the system as a Markov process, right? So the system, as what it does is you start from the initial state x naught, and from x naught, there are two possibilities. Either it reaches the next reach state safely, or some hazardous outcome happens in between, right, within the time frame. We assume the hazardous events as, say, terminal events. And so now we are interested in the probability that the system will travel from the initial state x naught to its terminal state xt without falling into a hazard state. So the equations there are the engine that drive the Markov process here. We basically, the advantage here is that we can calculate, given a reach set, we can calculate the probability of a hazardous outcome occurring within that particular set. So we know these values for p theta 1, for each reach set, from which we are able to evaluate the probability of the ConOps being successful. And we can, rho c basically denotes the probability that the ConOps can be successful. This is the place where you'd want to integrate severity if the severity of your outcomes are different, rather than a standard unity that we assume.
So I'll go through this really quickly. Essentially, we use that rho c that calculation of risk in a control optimization problem where we try to minimally adjust the controller gain of the UAV subject to this risk threshold. That risk threshold can be set by the operator. We evaluate our method in simulation for different hazard causes, and we find that for computing controllers, both online and offline, we're able to reduce risk at the cost of some increased distance to the target and increased controller effort. So to summarize, the potential impact for Preach can be a tool that the FAA uses to give guidance on how to do risk assessments. It's a way to practically implement risk assessments, given that all we need to do that are the drone dynamics and data to model hazard outcomes. We don't need that conditional probability data that classical risk assessment needs. And that leads us to be able to partially automate these Part 107 waiver requests. And through this partial automation, that can also make in-flight risk assessments possible and computation of safe controllers for UAVs. So, thank you.
Thank you.
Much happy to take any questions.
Yes, sir.
On slide 10, sorry. Your risk probability or risk intensity, is that symmetric distribution or is it a skewed one? Because, you know, sometimes depending on the winds, you might want to fly hedge to one side because the wind can push you. So I wasn't clear from that. The drift risk, was it assumed to be symmetric or was it directional?
It was skewed to essentially drift to the right here.
Can I?
How would
try?
How would you tell? Just looking at this, how would you tell?
Oh, go ahead. Yeah.
So I'm assuming what you're asking is what is the distribution of the points in the initial set, right?
Yeah.
Yeah. So in this case, as of now, we assume that given a reach set, the UAV is equally probable within that reach set. But as part of our future work, what we have been working on and what we're working on is to create a probability field instead of a simple reach set. Okay. So given the probability of given the distribution in the initial reach set, our initial findings suggest that if it's a linear time invariant system, then the variance of the process translates over reach sets, right? And one very simple way of visualizing that is that if you were to start in any of the corners or the edges of the initial reach set, you will notice that you always stay in the corners or the edges. So that's a property of linear time systems that we hope to exploit and create probability fields instead of simple reach sets, which give much more accurate results on the total risk.
Yeah, the reason I ask is because a childhood friend of mine flies drones, and he always comments that the novice drone operators don't hedge their breath against the risk and the gust that happen in the wind. So they basically think of placing the thing in a nominal position, and then they don't have any controllability left when you have gusts. And so that's an important aspect when you're trying to think about the trajectory.
Exactly. So if the UAV were equipped with Preach, it would automatically be able to do it, because here we have the hazard cost that we have identified as drift due to, say, sensor error. Yeah. But we have also generated hazard costs, say, wind hazard costs. Yeah. So if you have a wind distribution, then based upon that, it will create a reach set, right? Okay. So now the drone operator, or if it's an automated process, the system will identify that its reach set is within the hazard that you're trying to avoid. So it'll automatically shift itself so that it comes to a point where it's not reachable anymore into the hazard zone. Yeah, so that's something Preach addresses. Right.
Questions from our steering committee members?
Hi there, it's John Bernimo. I'm curious, did you guys work with or encounter or get a hold of any of the ongoing UAS risk assessment activity that the FAA performs, specifically like it's our target levels of risk rather than this variable proposed option? Have you done a comparison? Did you consider it? Is there a reason you took your approach versus that? And do you think it'll supplant what we do today?
So I'm not aware of the of FAA's work in the UAV space, but one of the things that the Nassim report identified was that UAVs, we have to consider this notion of de minimis risk when we consider UAV operations compared to general aviation, right? So I'm assuming that the tolerance levels that we seek for in general aviation are usually 10 power minus 9 or in that range. But for UAVs, that it has been, I think, recognized that that's not an achievable level of risk, or neither do we need to achieve it, considering the notion of de minimis risk. So yeah, I think I answered a question. I'm not sure if it was that question that you asked.
Yeah,
I would add that. Oh, sorry.
Go ahead.
I would add that we do in the future plan to do a sensitivity analysis comparing preach with the general classical PRA approach that we discussed earlier.
Yeah, exactly.
Thank you.
Thank you.
Yeah, a quick question from virtual. So again, I'm trying to understand, you talked about this as a tool for FAA to use, I assume, kind of in approving in some way, somehow, or providing guidance on safe flight paths. But then you're also talking about it being a real. Is this? Are you thinking of this as a real-time tool that an operator of drones would use to assess risk, or?
Actually, both. So
okay,
if
so
you
it is
consider,
both. Okay.
Yeah, if you consider the 107 waiver process, for example, right? It goes through a loop of risk, analysis and mitigation, and then it's like a 90-day process before FAA can come back and say whether your ConOps is a fly or no fly. By which time, the analysis that you have done, maybe you have analyzed the wind conditions, and then you have come up with the risk number, but that no longer holds true 90 days down the line, right? So we believe that this is because it can be done real time, and the reachability analysis itself can be done prior to the ConOps, because reachability basically depends only upon the system dynamics, the UAV's dynamics. It is the strength of the system is basically separating the UAV dynamics from the ConOps risk. So the ConOps risks are tied to this notion of hazard maps and hazard intensities. We calculate the risk of the process based upon the system dynamics that guide it over this hazard field. So it does a real-time control algorithm that can be used on the drone. It can also be used, say, by drone operators to prove, their claims of risk mitigation.
Okay, thank you.
We have about 1 minute if there's one more question. Okay. Thank you all so much.
We'll be at the poster if anybody has any questions. So, thank you.
All right. One more time, please, a round of applause for all the teams. This is that was a major milestone. You all have been working on these projects for some time now, and your milestones have been rather spread apart. And so you all just reached another one, and now we're going to quickly jump to another one. So we're going to take a break, and like I said, we have 75 minutes for the break. So it is currently, time zones are off, just after 2 o'clock. So that would be 3:15. But like I said, for those in the room, please don't go too far. Maybe after 30, 45 minutes, start to come back, because we do plan to wrap earlier than that, and come back and do the award announcements. Okay. Thank you, everyone. Okay. All right. So It is time after much deliberation. So Marcita, Acting Chief Data Officer of FAA, and Steve Bogucci from FAA will be announcing the winners. So when your team name is called, please come up and accept your prizes. And thank you, everyone.
Jamie's all red, so that's no indication of what just
Oh, I didn't.
in the background.
I had no idea. I had no idea.
But I do appreciate my steering committee. They were very thoughtful in the evaluation. As I mentioned before, we spent the past couple of weeks reviewing your technical papers. So today was just a great opportunity for us to hear from you and to do our final rankings and ratings on each of the teams. I'm a big proponent of diverse skills. So hearing some of the teams introduce themselves really highlighted the fact that to do this kind of work, it really does depend on scientists, engineers, folks who have experience on the operations side. We had pilots in the room as well. So I have high hopes about what the future will be, knowing that you all are doing this kind of work and have this kind of passion for the field of aviation. So with that said, we are now going to walk through the rankings of each of the teams. We'll start with our sixth place winners and then work our way towards team number one. So I'm going to be co-presenting with my co-chair, Steve Bogucki. So he will be reading off the winners. I will be here at the podium handing out the awards to the teams. And afterwards, we will be taking pictures. So.
All right, so we're ready to get started. This is a huge honor. I have so much respect for all of these proposals that I feel like it's the greatest thing to be able to announce the winners. So we'll start with the sixth place team. We're awarding 2 sixth place awards today. Both these are for $3,000. So for the first sixth place awardee, it's going to be Embry-Riddle Aeronautical University with their Sky Twin, a digital twin of the NAS for air traffic.
Thank you. Congratulations. Thank you.
Great, congratulations. So also in sixth place, awarding for $3,000, is going to go to Binghamton University for their assessing flight delays using weather predictions.
Congratulations. We'll take it in.
Yeah.
Yeah.
Congratulations. So awarding for fifth place, and this is for $5,000, is going to go to Texas A&M University for the reducing aviation emissions with MILP optimization.
Congratulations.
Congratulations. So for fourth place, this is an award of $10,000. This is going to the University of North Texas for their Weathering the Sky, GNNs for UAV micro forecast.
Thank you so much. Thank you.
Congratulations. For third place, this is an award of $15,000. This is going to the team of Oregon State University and Drexel University for PREACH, Probabilistic Risk Assessment using REACH.
Congratulations.
Congratulations. So they wanted me to make this one exciting. So for the final two teams, we're going to invite you both up to the stage with Marcita. So will the University of North Dakota and the University of Texas at Austin please both come forward?
Yeah. And there's no confetti coming from the ceiling. So.
No school colors.
Yeah.
Thank you. So we will first announce second place. This is for $20,000. Second place goes to the University of Texas at Austin for their AI-driven pilot, ATC Communications of Airport Risk. Congratulations, which means in first place for $25,000, big congratulations to the University of North Dakota for their sentiment and pattern evaluation of ATC keywords. Congratulations.
So with that said, congratulations to all the teams who had an opportunity to participate in today's event. Safe travels back to your destinations. And as I mentioned before, I hope this has been a great experience for you. So not only did the steering committee deliberate on the finalists today, they already started brainstorming for next year's data challenge. So I'm so grateful to have all these subject matter experts partnering me through this, and I'm looking forward to what's to come and hope to see either you all back or for you to just tell your other kind of students about your experience so that we can continue to do this and for it to be a great success. So thank you, everyone. Appreciate it.
Our budget is